The second galactic model, or GİLMORE device, we are lucky to say GİLMORE means young, young is, old is, spheroid, plus thick is. In that years, there was a conflict between radial distance of the star. Here is the galactic center, here is the sun. R0, the distance of the sun to the galactic cluster. X used here is the projection of R. Z is the vertical distance. Another R is the distance of the star relative to the sun. And L, B are the galactic coordinates. It is not difficult to write the equations giving info. Thus, we can express the densities which are given in X and Z and R. We can express them in terms of relative distance R and LB, the galactic coordinates. Now, a second set of parameters. What differences were between these models? One Cosomera model. According to them, at that time, the disk for disk, there were three alternative scale heights. H is the scale height. For the density, it was assumed 1. And for the halo or spheroid, the density near the sun was adopted as 0.002. For the second model, N1 and N2 are the densities close to the sun for the disk, and 001 is for the polar spheroid, and the scale heights for the disk was adopted as 0.1 and 0.3 kiloparsecs. For the third one, the difference is only the disk, the density near the sun was adopted as 0.02, and the scale height as 1 kiloparsec. On the right side, we have the logarithmic gradients of these models. As it is dependent on the galactic coordinates, this are problem for a paper of myself and Eker. This is M101. We can compare these models and see the difference. Now, in 19 8, we tested these models. We have two papers, one for Gerard and Salih, that was a Spanish colleague, and Salih and Gerard. In 1990, Salih published 4 papers and compared the densities estimated by using photometric models. Now we will see the comparison for 2 papers. The circles correspond to pieces density function in both diagrams. And the solid lines correspond to the densities estimated by the argument. Now, what is your decision? Is there an agreement between the models and the density functions estimated by the argument? The answer is the following. The agreement is for a limited of absolute magnitudes, especially when you look at the right side, we see this agreement. We see statistical disagreement. Why? Here, only absolutely faint magnitudes, 6 and 8, our densities are higher than this is. But for the apparently bright magnitudes, the case is the inverse. How could this problem solved? This is a problem, and this could be solved by the improved argument. Husserl in 1978 used theoretical data. Yes. It was synthetic data and improved this photometry. Here we see the equations, the transformation equations of Husserl. I mentioned about the transformation of Şahin. Now we have the first one. Husserl used here I will give you 2 diagrams. The left one is the 2-color diagram of Husserl, theoretical. Here at the left, one can separate the stars into 3 populations. His, Hindis, Sikhis, and Hero as a function of magnitude, now M over H in terms of metallicity, I need to say. And on the right, we have the magnitude color diagram, which can be used to the absolute magnitude of the stars theory. There are, on the right side, we have three color magnitudes. For this, for Lego, and for Tindex, for Tindex, and Halo. Now, let us consider the one, the upper one, for the disk, for the Tindex. There is a thick line which is familiar to every astronomer, but there are also two thin lines corresponding to evolved stars. So, one color index corresponds to more than one absolute magnitude. I estimated at home for the color 1.1 to minus R1.1 and the absolute magnitudes corresponding to this color index are given in couple 4.5 or 3.0. If it is evolved, if it is main-sequence star, 4.5. If it is evolved, 3.0. This is for thin disk. For thick disk, this data are 5.5, 3.5, and for the Halo, 6 and 3.2. Now, which one shall we use in our calculations? If we go back to our luminosity function here at the right, we see that the densities for main-sequence stars are larger than expected, so they must increase. We must find sufficient stars to adopt them as equals. This can solve the problem. Actually, that is what I did. And I reported it to Busa, because he was my boss at that time. And we published it in the first time in one of our papers, ÖNAL, KARAALİ, Busa, in 1990. This is the luminosity function estimated by the photometric, and this is the laser. This is the Zeki corresponding to absolute magnitude 4.5 does not disturb our result. This is not our fault. At this absolute magnitude, the isochrones are crowded. So, any small difference may choose a large difference in absolute magnitude. Yes, calibration with the Cambridge Astronomical Institute. We worked with Gaia Astronomical Institute for many years. In 1990, 1997 and in 2000s, I visited the Cambridge Astronomical Institute. GİLMORE was our referee of some papers and papers. So I had the courage to ask a collaboration to the partners. They accepted. And as I told before, I visited Cambridge Institute. We decided there to use the slow photometry. Slow photometry, the data of slow photometry are in CCDs, so they are accurate. So the story of photographic astronomy ended. The first CCD data were provided from Cambridge Astronomical Institute. The kinematical studies, we have kinematical studies that carried out to be carried out by Radial. And these wave data were provided from Cambridge Astronomical Institute. There are some common papers. I will not mention them because my chairman is also my student, ordered me to finish. Yes. We published, to my mind, sufficient papers with these two institutes. But we had also some different procedures in our faculties. Yes, for example, just a few examples. We improved some transformation formula. Here, the formula of Zeki et al. And the right one, KARAALİ. We estimated metallicities by using ultraviolet excesses of the stars. And I mentioned two equations for density functions, one for disks and one for spheroid. We thought, is it not possible to use only one equation? We did it. We used only one equation with two exponentials for the whole galaxy. But we didn't adopt the scale height as a constant value, but as a function of vertical distance. I am going to finish it. I want to mention from the paper of Radial et al., which was used to separate the dwarfs and giants by means of V magnitude of UVD and G, J, H, and K photometry, and last words. I was retired in 2006. My three students who are here this time, the present time, Sarah Güngör, Aksel Çokbilir, Esma Yaz Gökçen, accepted the responsibility to continue this collaboration with Cambridge faster. Today I see them very well, so I thank them. We are grateful. When I say we, I and my students, my institute, my department, if the chairman agrees, if the director agrees, we are grateful to professors Eker, and from the Astronomical Institute of Basel University, and to Professor GİLMORE from Astronomical Institute of Cambridge University for their collaborations and supplying data from our department. Also, we thank the Swiss National Foundation for financial support for many years, not for money. Basel Swiss National Foundation, not money. From the end of 60s up to 2000. My last thanks are to you, thank you very much, and to Selçuk to design this presentation. Otherwise, I shouldn't do it. Thank you.
Any question or comment? You can raise your hand. No? Okay, thank you. I have a few words. First, in the opening talk, I forget something. I am deeply regret to forget saying something about friends who have been stardust in a few years. You know, we have lost some colleagues in the last few years. Ahmet Devran, Gerard, Akif Esendemir, Zeki Tüfekçioğlu. I am despairingly remember them. Allah rahmet eylesin. I have two announcements to make. First, before the lunch, we will take a meeting photograph instairs, just adjacent to the hall. And we have a reservation for 30 persons in Professor's House, which is a restaurant in the garden just adjacent to the historical gate of the university. People who want to have different dishes can find good restaurants in near Süleymaniye also. Okay? Thank you very much.
Am I allowed to go?
Sorry?
Am I allowed to go?
Yes. Now we have a coffee break for 15 minutes. Okay?
Available to analyze, to do science with that. And this is particularly the Gaia mission, and the bottom line simple version is 1 billion pixels, because it's a very, very big camera, the largest camera in space, for 1 billion stars, which is a very large number of stars. And as you can see already from the pictures up there are 3 different types of data, which I will introduce shortly.
The largest section on Gaia's camera is the astrometric field. As the image of a star moves across its 9 columns, each CCD measures the star's position and brightness. Then the starlight passes through 2 special prisms that direct different wavelengths to the 2 columns of CCDs in the photometer. This provides information about the star's temperature, size, and chemical composition. Light from a subset of stars also reaches the radial velocity spectrometer, 12 CCDs that are used to measure how fast stars are moving.
So that's a quick overview of the Gaia mission. You see there are 3 different types of information summarized again on this page here. There's the direct imaging of the whole sky repeatedly, which gives the brightness and the positions of the stars. And by repeating the measurements over what will eventually be more than 10 years of data, one gets very accurate parallaxes and prop motions for the stars. And in the middle is the radio velocity spectrometer. There's going to be a special talk about that this afternoon. I'll take more. And at the bottom is probably the most important new part of Gaia, which is the low dispersion spectroscopy. It's interesting that this is precisely the thesis topic of Professor KARAALİ that he introduced a few minutes ago of slightly defocused spectroscopy. Except now, instead of doing 20 stars in the bright star cluster, one does nearly 2 billion stars repeatedly. There's an enormous amount of information in that low dispersion spectroscopy, which is yet to be exploited. Now this slide and the next one, themselves very old slides. These are two of the slides I presented in the year 2000 when to have the Gaia mission approved and adopted by the European Space Agency. So we'd spent the previous 7 years in the science team working with industry, developing both the science case and the technology plan for Gaia. And in the year 2000, there was a big meeting in Paris where I was able to present the proposal for Gaia for approval. And the talk clearly succeeded because we got given €1 billion to build the mission. That's a lot of money, and it succeeded. But you can see the list of the primary challenges. So what is Gaia all about? It's the red text at the top, origin, formation, and evolution of the galaxy. That is the primary challenge, primary mission for Gaia. And the list underneath is all of the specific things that one wanted to do. But in addition, and this is another second slide from that same presentation, there is a list of all of the specific questions that one can ask for stars inside the Milky Way galaxy. But also there's a very large amount of information about our local part of the universe, but also from luminous sources, supernovae, and so on. One can do cosmology out to very substantial distances. And one of the big exciting things people are doing currently with Gaia is gravitationally lensed quasars for an accurate determination of the Hubble constant and the large-scale structure of the universe. In addition, I'll show you briefly one slide later, Gaia, because of its precision, is testing general relativity to much higher levels of accuracy than had previously been possible. So the whole range from fundamental physics through solar system asteroids to large-scale structure of the universe down to the asteroids in the solar system, all part of the project. So it's a huge challenge. So now a little background. On the left-hand side here, you can see the first ever published Hertzsprung-Russell diagram. It actually dates from 1920. The Hertzsprung-Russell diagram was already 10 years old by then, but this wasn't the normal way of presenting it. So this is from a review article by Henry Norris Russell in 1920, which was the first presentation of the Hertzsprung-Russell diagram in the way that we now use it. And on the right-hand side, you can see what we knew before Gaia. This is the local stars from the Hipparcos mission, 2005. And you can see there's a very good representation of intrinsically luminous stars, young blue stars, local giants, running down through the sun and making it into a Lake K star, but nothing fainter than that. So that was the state of the art before Gaia. And this is where we are now. So you can see this is about 1% of the Gaia catalogue that's published already. And this is just very nearby stars. If I plot too many stars, you can't see anything anymore. But you can see in the top left the same part of the Hertzsprung-Russell diagram we had earlier. But now the sequence goes all the way down to below the luminosity of the faintest white dwarfs. So for the first time ever, we're sampling the entire stellar populations near the sun. There's an enlargement on the top right of the white dwarf Hertzsprung-Russell diagram, which you can clearly see by eye the two sequences, hydrogen white dwarfs and helium white dwarfs. And in fact, if you look at the black dots, you can even see the binary microwave sequence. And there's a whole separate sequence of cataclysmic variables, which are very common. And in the bottom right, you can see, again, this is the successor to a figure that Salih KARAALİ showed. This is the metallicity dependence. So this is a sequence of globular clusters color-coded by metallicity, with red being the high metallicity and blue being the low metallicity. So this is the metallicity dependence of stars, all of a single age. And that's just a trivial illustration. When one has such a large amount of such high quality data, you can select how you look at things. You don't have to model everything out as we used to do. We can choose just old stars and look at how they depend on metallicity or on velocity or something else. Or we can look at a particular metallicity range and see how things change with age. So I'll give you a few illustrations of how we do that. The first is an interesting historical point. Everybody knows that the Hertzsprung-Russell diagram was developed by Hertzsprung working in Leiden at the time, and particularly by Henry Norris Russell, and was the beginning of the dominance by the United States of astronomy in the 20th century. So this was when astrophysics moved over to North America and Europe got left behind. But what actually happened is that the project was started in 20 years earlier in Cambridge, England, as a deliberate project to go and measure parallaxes for bright stars using the exciting new precision technology of photography. And so, as always, doing something new, it takes a long time. You never have enough money. Eventually, the money was provided by a wealthy woman, actually, so they've forgotten that rich benefactors for science have always been women. And so this first telescope, Sheepshanks telescope, was named after Anne Sheepshanks. There it is. It's not there anymore. It was destroyed and thrown away in the 1960s. But it's been half a century measuring parallaxes. And you can see on the left-hand side that the program was very successful. They were just about to start publishing the results when a young postdoc turned up from the United States looking for a project. This was Henry Norris Russell, and so he was given the project of writing up and publishing the parallax program. And so it's a nice illustration of how the people behind the program have been working for 25 years to collect the data, and then a clever young postdoc takes all the credit. And I hope that many of you in this room will do the same thing with Gaia. So I might have been working on the project for in fact 35 years, but need you, the young people in the audience, to take the data and turn it into science and become famous because of it, to leave the legacy of Gaia behind. So I hope that I will become like Mr. Hinks, hardly remembered except by historians, and you will become famous astronomers. Now I'll show you a few illustrations of Gaia data. Here's one example from stellar evolution. It turns out that star clusters are more complicated than we think they were. That's surprising. You get better data than these nice little star clusters that are defined by a single isochrone. Beautiful things. We all work on star clusters. We all know that they're all the same age. Well, they're not. And in fact, the picture at the top right shows the apparent width of the turn-off as a function of the age of the cluster. So you can see that as clusters get older, the age range of the cluster keeps increasing. Now that's impossible, because the young cluster with a narrow age range can't keep forming stars. There's no gas there anymore. So how is it that stars, clusters look like? They're changing their ages as they get older. And the answer you can see, because from the Gaia data, the black dots there and the red isochrones, the black dots are scattered all over the place. We always used to assume it was just measuring error, and so we moved all the data points so they're all lined up. But in fact, it's not measuring error. The Gaia data are so accurate that they are accurate. There is a big scatter. And in fact, the thing that was wrong was our assumption about the way stars evolve. And so the red isochrones and the black isochrones there, a set of isochrones of stars, all of the same chemistry, all the same age, but with different internal rotation. So it turns out there's another factor, another parameter in the way stars evolve, we've never studied before, which is the rate at which the core is spinning, which turns out to be just as important as anything else. And so it's an illustration of how simply having good data means the assumption that we've been making for 100 years. It's called the Vogt-Russell theorem. It's been around for more than 100 years. That to describe a star, all you need is its mass and its chemistry. Wrong. You also need to know how fast the interior is spinning. And so that's one illustration of how, when you get good data, it's harder to analyse things, because things that we never had to worry about suddenly become very important. Now I'll give a couple of examples of galactic astronomy. This was again introduced by Professor KARAALİ. There's a cartoon the cartoon is from Wikipedia, showing what our current view of the Milky Way was. You heard the story of how through the 1980s the picture changed from just the thin green line to the yellow, the existence of the thick disk. On the right-hand side is the original discovery paper of the thick disk by myself and colleague Neil Reed. That's become a classic since and turned out to be a very good description of the way the galaxy is built. But what we really want to do is carry on now with the cartoon on the bottom and say, how can I add yet more information so I can be more precise? Counting stars is good, but we want to do more than just count stars. We want to know how they're moving. We want to know how far their radial velocities. We want to know what chemical elements they're made of and all the different chemical elements. With chemical evolution is now the big challenge. And for that we really need also ages. So what can we do when we start to be able to get that sort of information? Well, first let me remind you of on the left-hand side, this was introduced a few minutes ago. This is the Sloan photometry or high latitude field. This is star counts. And you see on blue on the left-hand side of the left-hand figure is the halo and thick disk, and on the right-hand side is the thin disk. And on the right-hand panel is exactly the same stars, but now that's in infrared photometry. You don't see the simple distinctions at all. But just to help you see what's actually in the left-hand panel, that grey line, see there's two vertical grey lines. That grey line is the thick disk turn off, and that grey line is the halo turn off. So the advantage of Sloan photometry is just by eye. Sloan is so sensitive to negativity. Just by eye you can see the difference between the halo and the thick disk. And there it is in front of you. And this was the basis of the collaboration, very successful collaboration, and the way in which people studied the structure of the Milky Way galaxy from about the 1990s up till a few years ago, up until Gaia. And this is an example of fitting to it. This is probably the last such example that's ever going to be done. This was only from earlier this year, just a couple of months ago. But this is fitting the star counts from the Dark Energy Survey. So it's a survey of about half of the sky, particularly high latitude sky, very high quality data, very deep, very well calibrated, a huge team of people involved. And it fitted essentially exactly the same model that Salih told you about. So it fitted it to hundreds of millions of stars across very many fields rather than a few lines of sight, and established the basic structural parameters of the Milky Way. So this concept of doing large-scale, what are the properties of the galaxy has probably been done. It's now fairly well established as to what they are. So what comes next? Next comes Gaia. Now Gaia data are wonderful, but they're not simple. That's the key, is that every stage as the data get better, they also get more complex. And so the sort of analyses that we need to apply also get more and more complex. And so you have to worry about these three different types of errors. Because the data are so precise, there's now an important difference between random errors and systematic errors and correlated errors. These are things we never had to worry about previously because random errors just dominated everything. And now they don't. Random errors are now negligible, and so one has to worry a bit more sophisticated about statistics. And as an illustration on that, on the figure on the right-hand side, you can see this is from an analysis I've been doing with one of my colleagues in Cambridge. This is a HR diagram on Gaia photometry for nearby high-quality stars towards the galactic poles. And the vertical, the green band is where the stars are, and that's for most of the diagram. The black lines are the scatter, the error. And again, you get this point, which again made by Salih earlier this morning, is that when you're close to the turn-off, stars can have two possible values of absolute magnitude. You're either on the subgiant branch or on the main sequence. And telling them apart just from parallaxes is very, very difficult. And so it's really important that one remembers this distinction. So that's the systematic error. Much longer black vertical lines near the turn-off due to this fact that everything's quite well. So what can we do to try and worry about that? Well, the most important thing is that with Gaia accuracy, it's no longer possible just to say the distance is 1 over the parallax. It's fine, you're not very accurate, but when you're accurate, and in particular Gaia parallaxes where the stars are quite far away, the parallaxes are very small, so just by chance, random errors, some of them become negative. And that's unphysical, you can't invert to get a negative distance, so you have to do something more sophisticated. And the techniques involved now, Bayesian priors and probability distribution functions, all this terminology that we never had to worry too much about very long ago. Fortunately, there are a subset of the community who have made their living out of producing public domain Python computer language packages that do all this complicated stuff for you. So it isn't necessary for everybody to try and reproduce the whole of Bayesian statistical probability theory, which is a relief because it's taken a community of hundreds of specialists about 15 years to do it. It's just currently beyond the capability of a single individual to actually analyze Gaia data. But the tools are there, they're in GitHub, they're public domain. So that is the approach for the next generation of analyses, is to build on what others have done. Don't try and start from scratch the way that Salih and I had to do when we were young. That was a long time ago. So now, another couple of examples. Here's an example of what happens when you combine Gaia data with Gaia ESA, which is a radial velocity survey and monitoring project that I lead. So this is with precision, very high precision radial velocities with accuracy of a few tenths of a kilometre per second. And these are just two maps of the sky, in which the right hand, it's a star-forming region, the right hand picture just shows the coordinates on the sky and colour-coded by radial velocity. And you see there isn't an obvious pattern in the radial velocities, so you would say, well, this is just a big cluster with stars moving all over the place. But on the left-hand picture, when you add proper motions, you discover, well, actually, there are systematics there. The stars are almost all moving left to right. They're not moving up and down at all. So instead of a picture that we had previously of star clusters being basically round and just evaporating as they evolve, what we have here is a picture of a star cluster that's being stretched along the Milky Way by the tidal field of the Milky Way. But also, if you look hard, you see half the arrows are yellow and half are blue. So what is here is actually two separate clusters, two separate things, living in exactly the same place at almost exactly the same age. And they're starting to separate into two separate clusters. So we're watching a stage of cluster formation which we've never seen before, which is a whole complex breaking itself up into coherent kinematic groups. And this is an example of the future of young cluster research. Young clusters, horribly complicated things actually, but it's a big field of science available there. This is just one example. So another example, going to the other extreme, what can we learn about dark matter? And dark matter, of course, is a big exciting subject, and people have tried for a long time to find out what it was. In the figure there, with an enlargement in the box, is the lower part of the figure, is the measurement of how much dark matter there was near the sun, or there is near the sun, as a function of detected measurement. And you see that up until about 1990, measurements are all over the place. And that's not surprising, people didn't have very much data. But then starting in 1989, you see on the left-hand side of the box, a blue point with a very small red uncertainty attached to it called kg. That's the Gilmore determination of the dark matter in the sun. And that used the thickness density and radial velocities to determine it. And you can see, again, just looking in that grey band, that every determination since then has been consistent with that number. So the most accurate number we have actually still dates back to 1989. And you think this must be something that Gaia is going to do better, because what we had in 1989 was photometry derived from photographs that we had to calibrate, and a small, relatively small number of radial velocities. And we developed a new, very sophisticated mathematical modelling technique, which now everyone uses, so that's the same. But the point was the data set we had, the same data set that led to the discovery of the thick disk, was very old and very small. So you think Gaia must be able to do a lot better than that. So why have you not been seeing papers from Gaia saying, here's a new determination of the dark matter? Well, here is the reason, here's the explanation. So at the top of the equation there is just the usual pressure-gravity balance equation, which you use to determine how much dark matter there is. That's the equation that Hight and I devised and developed a new method of solution for. But it's standard, it's just physics. At the bottom, the panel there, are the Gaia results towards both galactic poles, still not published. And what you see, the blue histogram is one particular subset of the data. The way one does these things now is there is a very large number of black curves you can really make out there. These are the Bayesian inversions of all of the Gaia data that I mentioned that one does. And also there's the red points that come from the Sloan data analysis just on the North Pole, which is the left-hand side. And you can see the red lines, the solid red lines, are a fit with the parameters there, the thin disk, thick disk, and the normalization, which is essentially the original GİLMORE model, and it just fits the Gaia data ridiculously well. So I think we were really just lucky. We tried to be very careful with our photographic calibration in the 1980s, but we got it absolutely perfect. So even Gaia data were 200,000 times more accurate than we had. It's exactly the same result, which is really quite exceptional. And this is why you haven't seen new results. This is the only case I know of where a pre-Gaia measurement turned out to be more accurate than Gaia can do. All the rest of modern science has been changed by Gaia. There's in one case that hasn't, strangely enough. So now let's come back to our cartoon of what happens when we add more information, radial velocities, ages, histories, chemistries, and so on. And so what we really want to do now is galactic chemical evolution, which we'll talk later on too, actually, on the importance of galactic chemical evolution, and I can't but support that concept very strongly indeed. Adding chemical evolution to the structure of the Milky Way is the way to determine new information. And here's an example of what one needs to do. So now you measure chemical element ratios, usually it's one of the alpha elements that come from type I supernovae, something that changes very fast, as a function of metallicity. And what you see on that right-hand diagram there is that there really is a very large number of stars which are much more retrorich than the Sun, further near the Sun. So, a very obvious question, where did they come from? The interstellar medium of the young star clusters forming today have roughly solar metallicity. So where did these stars with 3 times solar metallicity come from? They can't have formed from the local interstellar medium because that isn't that rich. So where do you go to find stuff that's that metal rich where they might have formed? And the answer is you have to go all the way into the central kiloparsec of the Milky Way. And so we are then forced immediately to say that a very substantial number of the stars near the Sun actually formed in the central regions of the Milky Way and got flipped out where they are today. It's doubly interesting because these very metal-rich stars are those that have exoplanets around them. That means most of the exoplanets we're finding actually formed in the inner regions of the Milky Way, and their parent stars got kicked out to where we are today. And in fact, our Sun must have formed a kiloparsec or more interior to where we are now, and we got kicked out too. So that's an interesting challenge when it comes to understanding galactic structure, is the part of the stars that are currently near us in the Milky Way didn't come from here. They came from way interior, and they've been kept out through this process now called stellar migration, which it seems is really important. So galactic chemical evolution is very challenging. It gets even more challenging from results like this. So if we look just at the right-hand panel, top square, this is data partly from this and partly from Gaia. And so the top square plots the metallicity, ion abundance versus age, and there's no correlation at all. So at every age you can find stars with a wide range of metallicity. At every metallicity you can find stars with a wide range of age. So this is this complication I said before. In Gaia you can slice it both ways. And when we do that, you get the huge scatter. But if then you plot below that, figure 3, if I look at element ratios versus age, there's no scatter at all. So this is completely inconsistent. Top one says that at any given age I can have a very wide range of metallicity. Bottom one says that at any given age I've got no scatter at all in element ratios. So this is the real challenge for galactic chemical evolution, which I'm looking forward to hearing more about this afternoon, is that wherever you are at whatever time in the Milky Way, you always see the same pattern of chemical elements, even though you've got very different ion balances. So a metal core star always has the same pattern of chemical elements as any other metal core star, no matter what age of format, and vice versa. And I think this is the really big challenge that we have to understand. However, we are making some progress. And again, this comes largely from the Gaia ESO survey. It's an example on the left-hand side. This is a modern version of the thick disk plot. So you've got an element ratio, alpha to ion versus metallicity on the left side, and you can see the upper branch, which is the thick disk, and the lower branch, which is the thin disk. And now the data is so good, and there's such a lot of stars, you can just see by eye. You don't have to do the complicated modeling that we did. But with Thomas Masseron, a postdoc of mine a couple of years ago, we developed a way of calibrating ages for giant stars by measuring the carbon, nitrogen, and dredge-up. So the element ratio of carbon and nitrogen changes with the star when it's on the giant branch in a way that depends on its mass, and mass depends on age. And so we can convert chemistry into ages directly. And that's the right-hand plot there. This is from a paper that was published 2 days ago from the Gaia survey in strong advanced physics. And you can see from the colour coding that the thick disk is older and the thin disk is younger. So you can see immediately the history of the Milky Way. So let's go on and look at that in a little more detail. But here, just in the interest of time, we'll look just at the left-hand top plot with all of the data. This is essentially the same as before, in which the upper thick disk stars are inside that big black line, and the lower thin disk stars is a very clear distinction. But now we can add ages to that plot, and we can actually watch the Milky Way evolve. So that's the age sequence. And so now the data is so good that just by eye, we can see that the oldest thing in the Milky Way is the thick disk. The thick disk took a couple of billion years or so to form, and it enriched right up above solar. Some stars in the thick disk, the inner thick disk, are above solar. And then there was a big merger. A large amount of hydrogen was added, so that diluted metallicity down to the beginning of the thick disk, the thin disk. And so the remnants of the thick disk enriched the thin disk, which then evolved separately. So you can see immediately there's a double evolution of the Milky Way. It's been suspected for a long time, but now we can just see it by eye as of earlier this week. Quite remarkable. Now, a couple of other examples of things you can do with Gaia. Who was one of the first results from the second Gaia data release, several different groups got the same result, was the direct evidence for the merger that I just mentioned that terminated the evolution of the thick disk and started the formation of the thin disk. So it converted the proto-Milky Way, the basic thing that was there before the Milky Way, into what is now the Milky Way. And you can see it particularly just from the astrometry. That's the right-hand diagram there, where the vertical plot is circular motion, and so stars above the dotted line move up on orbits, disk-like orbits, and so you see the big blue ball, that's the galactic disk. Stars below the dotted line halo stars, you see they're much more spread out in radial motion than they are in circular motion. So in radial motion, the stars go across the range of velocities of 600 kilometers a second, whereas in circular motion, the range is only about 100 kilometers a second. So the orbits are all very, very radial, 6 to 1. And this is the direct evidence that those stars were on a galaxy that fell into the Milky Way on a radial orbit almost exactly to the galactic center. So in fact, that picture that's on the left there is this happened today in 2 other galaxies. It must be what happened to our Milky Way about 9 billion years ago. So one can see immediately here from the kinematics the history of the Milky Way running in astrometry. Quantifying this and moving on is the next big challenge for astronomy. Just one more example of this large-scale properties. Many of you will be familiar with these pictures, field streams that call of the stars in the northern sky. You take away all the rubbish, like galaxies and things like that, from astrometry, and just look at the important things, which are the stars, and you colour code them by distance, and then you see immediately the stream, the double-tailed stream across there. That is the tail, the tidal tails of the Sagittarius dwarf galaxy, which another student of mine, Rodney Barter, and I discovered in the early 1990s. It was a very exciting time for galactic astronomy around then. And so this is the evidence that galaxies are still merging with the Milky Way today. And there you can see the outer halo forming as these tidal tails wrap around the rim behind. But with Gaia, it turned out to be possible to measure the proper motions of these stars in fact, that thin, you can see it as a thin line, thin tail of stars, which was called the orphan stream because we couldn't find where it came from. It doesn't have a parent. In fact, it doesn't have a parent. The parent's completely dissolved. But with Gaia, it was possible to trace the orphan stream across the whole sky, and that's the one plot there. And what you would expect in a stream of stars is that the stars are moving along the stream, just in exactly the same way as the water actually has to move along the river. It doesn't move sideways and pile itself up on the banks. But strangely, these stars are moving sideways. So that's the proper motions in the bottom plot there. And so the stars that are in the stream, the entire stream is buckling. So you think, well, the only way a stream can buckle is if something is pulling it. And the only thing available to pull is the gravity. So it must be the mass of something that's pulling the stream. And in fact, it is the Large Magellanic Cloud. The stream goes past where the Large Magellanic Cloud was long ago when the stream was there. And so what we're seeing in those grey arrows is the tidal force of the Large Magellanic Cloud. And that means that one can actually weigh the Large Magellanic Cloud. So the equivalent experiments that measure the dark matter locally, except on the whole of the Large Magellanic Cloud. And this is unique in astronomy. It's the only time we have ever been able to measure the total mass of a galaxy. And normally galaxies just disappear, just run out of stars, but there's still plenty of dark matter out there. And we've got no way of measuring how much dark matter there is. So this is the first time in the history of astronomy we've known how the total mass of a galaxy. And that's from a couple of months ago. Then there's an interesting contrast. That same team during the same time also discovered some new dwarf galaxies. And that's on the right-hand side here. So the Milky Way picture is there just for scale. So these are 2 pictures to scale. On the left is the Large Magellanic Cloud, we just measured the total mass of. On the right, you can see that smudge. It's a very, very low luminosity galaxy called Ankyra 2, was discovered just earlier this year from Gaia data. And Ankyra 2 and the Large Magellanic Cloud turn out to be about the same size. So this is a real scale picture. Even though the Large Magellanic Cloud is about a factor of 100 more massive than the Ankyra galaxy. And it has 10,000 times more stars in it. So Ankyra is a very low surface brightness galaxy. We have 2 things exactly the same size. One of them has 10,000 times more stars in it than that. Any theory of galaxy evolution would tell you that's completely impossible. So this is an example of a new exciting thing. We don't know the answer to this. It's an open problem. So there's an example of one of the many new things coming out of Gaia, which is just challenging our understanding of what we think we knew. Now, how much time have we got? to what, about 4 magnitudes brighter. Then when people went to look at what it was, they discovered actually it was archival space infrared geometry, because no one had noticed, but it actually got brighter a couple of years earlier. This is in fact a very young star formation. They're rare, people are rare stars, only 25 known. And this is the first one ever where people have been able to discover both the optical and the infrared flux change, which is enormous. It's many, 4 magnitudes this thing's changed, and it's still going. And this allows for the first time to answer the question of what came first, the star or the disk. And so when stars are young, they're still growing, there's a disk, there's material around them, they're still falling on the star. And the question then was, does all the material fall on the star, which then becomes a star and blows away material and makes that? Or does it happen the other way around? You have a star, the disk dominates and falls on it. And in this case, it's clear that the disk actually is controlling the star. So the fact that it got hot, we read text to ourselves, it got hot before it got bright, means that the disk started falling in and was heated before it fell in sufficiently far that it dumped a lot of material onto the star to make the star more massive and more luminous. And so we see the outburst. So this is a direct detection of the early star formation process, again from Gaia data plus some historical splits of data. Here's another example of time domain astronomy with Gaia. This particular one is a gravitational micro lens. The system is lined up there. In fact, it's also an astrometric system, so because you can see it moving around the micro lens, and so the Gaia astrometry, which is the extra information you need to do the modeling, turns out it is one of these star and the line of sight. But the other important thing about this is, I hope you can see on the vertical scale up the top left, this star got up to 12 magnitude. And so this is not unrepresentative of the discoveries that Gaia is making. And you can to quantify this light field, there are about 5,000 data points in that light field. But this, again, illustrates a talk that you're going to get later today of the importance of small telescopes, a large number of small telescopes for following up the Gaia data. So the Gaia can only observe a star when it happens to be scanning that part of the sky. You need a large number of half-meter and 1-meter telescopes dotted around the whole globe, bringing all their data together to be able to understand what's going on. So there's another talk on that later on. I think this is a really important lesson from Gaia, is that Gaia needs a lot of small telescopes to work out what Gaia is doing in the time domain stuff. So there's an enlargement of the same things that you can see there. I haven't got 12 minutes, but these spiky changes in peaks of the microlens and cusps last about 20 minutes. So this isn't something we have one telescope taking integrations, so you can miss the whole thing. It's changed by a magnitude during a single integration, so you need a large number of data points. And so there's a huge future for all this sort of thing. This is, I won't say much about this, George will see what this afternoon will probably tell you. This is again some time domain data from the radial velocity spectrometer. So these are some emission line BE stars. And is an example of how much information is in time domain. Some of these stars, particularly the ones on the right-hand side, that suddenly becomes emission peak for no reason at all. But even with the Gaia data, you can't see the total flux changing. Clearly something's happening. So this extra information from spectroscopy is enormous. So we'll do more about that in a separate talk this afternoon. There's another example of the sorts of things we can do, like with a project that I've just been doing with a student down in Harlech, is looking at gravitational waves. This is the effect on the sky of a dipole gravitational wave. You have to be careful watching this thing because people get ill. Sometimes it's like flying a plane with turbulence or being on a boat with big waves. It's really set this stuff. But the entire sky is moving like this. And the amplitude is quite large for the expected background of gravitational waves at very low frequencies. These are not the ones that light can detect right now. Those are from small black holes. These are from supermassive black holes merging. The amplitude is actually, for an individual star, is only about 1,000 times below the Gaia detection limit. So it's about setting. So a next generation mission will actually be able to detect these individually. But now it should be able to see them statistically. And so there's a huge future for testing general relativity in a regime where there is no other way of testing it. So it's kind of fun going back to my youth and playing with general relativity and done that for a while. Now, last two slides on the future. There's a huge amount more to come. So far, we've had only 2.5 years of Gaia data, and only astrometry and only partially calibrated broadband photometry. And there's a lot still to come. The current lifetime of the Gaia mission is 5.5 years from now. So it's going to keep operating until the end of 2024. Subject to funding, but it will be funded unless it fails. And you can see on this plot how much better the data are going to be. So the problem oceans, compared to what we have now, are going to be more than 1,000 times more accurate. So it's a huge increase in accuracy as well as in numbers. The full Gaia catalogue contains something like 3 billion sources. Not all of those will ever have good data because they're often very crowded fields and it's easy to sort around. But there'll be a minimum of 2.5 billion sources per data coming out. And the final data won't be published till about getting on for 10 years from now, so there's a future there for you young people. You won't need capital, long gone and out of your way. And so there's a huge future in accuracy there. But also, more importantly, in the types of Gaia data that aren't published at all yet. So the coloured picture there are the spectra, the low dispersion spectra that you saw on the movie right at the start. And what you see there, those are single stars. This is time domain measurement of an AGD star, carbon stars. So there's an oxygen star and a carbon star. And this is how single stars change during their pulsation cycles. So this is just one star, and you can see that much information. And in the bottom plot is just for the large magnitude cloud, just to show you how many of these stars there are and how different their astrophysics are. And on the right-hand side is the evolution of a single supernova. So at the top, just after the supernova event, is just a hot featureless plasma. As it cools down, you get the lines of the newly created chemical elements being generated. So this is the factual input that you need for mapping chemical evolution. You can actually watch the chemicals, the chemical elements being created and dispersed. So all this is still to come. Just to say where we are now, this is to just remind people really that Gaia is a big data mission. So these are the numbers as of 2 days ago. And so you see there's 1.3 trillion measurements already. And Gaia is less than halfway through its lifetime. So we're already, this is the stuff we're processing in Cambridge and a couple of other data centers around. 1.3 trillion measurements that we have. That's a lot. That's a lot of light years. It's everything in the sky. It's got a lot of light years. And even the spectra that George will talk about is a very significant number of those. It's a big number. How hard in good old days we used to get spectra 1 at a time or 100 at a time, even 1,000 at a time in the state of the art, or up to billions. There's an awful lot of information in there. All that is available and will keep coming. And so I'll end. So here's a little movie showing basically that everything in the sky moves. I couldn't resist the temptation to get Galileo's cameras in the fog. And now we're going to zoom in. And it'll look like there's something wrong, but it's like an ant's nest or something because everything is shimmering. And actually, that's because everything in the sky is moving. The Gaia is so sensitive, it detects everything moving that it can see. So with that, I'll stop there. Thank you.
Thank you very much. It seems that Gaia is changing the rules of the game in so many years. There is also an important message in this presentation for our students. Do not get data as they are in tables. And ask if they include systematical errors. Okay? Any question or comment? I will ask questions to the students. So, could during meeting.
I mean, these last spins are so exciting. Can you repeat what it was about? Although you
Yes,
never
okay.
needed it.
This is the movie of the Gaia setting data release, so real data. So it looks like a picture of the sky, but it isn't, because there are 1.6 billion sources in there, and that's more sources than there are pixels on the screen. So if we just were to plot all the data as one pixel, one point, you just see nothing but white or black being a polygon. So this is actually a five-dimensional image, five-dimensional model, measurement actually, of the Milky Way, projected onto the screen as it would be if you were looking at the sky. But it's also time domain. From what you see there is the proper motions over the next 100,000 years for each of the sources. And so you see everything moving. And so this is how the nearby bright stars, of course, move all over the place, but everything moves. I should say that I've left these movies and the slides with cancelled, and so they are available for your reference and record and use here, so you can go through them a bit more slowly and see what's in there.
One of your slides you said distance is not 1 over parallax, or parallax is 1 over distance. So how can you calculate the distance?
Yes.
Yeah, so is there a simple way to calculate, or it's too complex?
Well, the answer is one of those annoying answers, and it means it depends what you mean by the question. So if you are looking just at a single source, then the distance, the best estimator of the distance is actually the inverse of the parallax. But if you're looking at a group of sources, for example, a star cluster, the best estimator is not the average of the distances, it's the average of the parallaxes. So you have to average in parallax space and then invert it, not turn everything into a distance and then invert and take the average distance. That gives you a systematic bias. And if you're working very close to zero parallax, just because the errors must be biased because there is no such physical thing as a negative parallax, then you have to do some sophisticated modeling of the error function to get the best estimator of the distance for a very far away source where the parallax is very small. Fortunately, as I've said, there are published routines. Quite a lot of them come with the Gaia database. There are easy to use routines in there that allow you, depending on what you're trying to do, to get the best estimator of the distance. But we agonised over whether or not to publish a list of distances for stars. And because there isn't this simple connection between parallax and distance, there is no official Gaia catalogue of distances. But there is an unofficial Gaia catalogue of distances, which is published by part of the team. So there are various databases, places around the internet, where you can go and say, how far away is this star, if that's what you want.
You still can use 1 over parallax for this.
But only in simple basis. Only in simple basis.
In one of the slides, you show the effects of gravitational waves on the sources. I was wondering what the size of the window you were showing us, or scale of it. I couldn't understand. What are we seeing
Okay.
in here?
This is a simulation. Not simulation, it's actually a calculation of the real data. So instead of having the whole 1 billion Gaia stars, the average number of stars in each little area of the sky is represented by a single dot. And then what you see is the quadrupole, that's the movement like that, distortion of the entire sky for a gravitational wave coming towards us from any direction that's symmetric, so it doesn't matter. Now, so that you can see it, the amplitude of this event has been increased by 17 orders of magnitude. So this is just illustrated by eye. The actual magnitude of the effect is about tens of nanoarc seconds for an individual star. But when you have 1 billion stars, you can average across the whole thing, and you can see this as a systematic statistical pattern. Perhaps the point of the paper is the last one, which we're referring right now, is that actually this allows us to test general relativity with very much higher accuracy than has ever been possible before. Because what we see there is the polarization. In general relativity, there's a very restricted polarization set. There are 6 possible polarizations. The general relativity has only 2. And so you can then do tests for those other 4 types of polarization and say, is there extra evidence for going beyond general relativity? And Gaia is actually by a long margin the most sensitive way to do that. And our latest paper shows we can not only do that, but by cross-correlating Gaia with pulsar timing arrays, we can increase the sensitivity of the pulsar timing arrays by an factor of 10. And we also test the speed of gravity 10,000 times more accurately than is currently known from the merger of the neutron stars. So it's surprising how much extra information there is at these low frequencies. And that's because the speed is a group velocity dispersion, so it depends on the frequency we're observing at. So the typical wavelength of the waves, the gravitational waves we're looking at here is about a year. A very long period of things, not these millisecond chirps. So we gain that factor in seconds from a millisecond to a number of seconds in a year. It's 10 to 10. So that's the sensitivity gain you get from going to low frequencies. So it's a fascinating general relativity there. Yeah, so we had a couple of papers in the physical review letters describing this stuff.
Okay. Question?
The last slide, why is it so exciting in the sense that did we not expect such motion? One thing. Is it because the new measurements are so precise so that we are able to distinguish every movement, every motion? Or is it because, as you have said before, motion is from inward, from inner regions to out regions?
Okay, that's a very astute, very clever question. The real answer is that actually there's nothing new in this movie at all. The real important point from this movie is that Gaia does actually work. So we have been able to see exactly what we expected to see. And in addition, which is almost everything you can see there now, but in addition, there are a few small subtle things there that we're not expecting. So we can measure, for example, the distortions due to the gravitational bar and the wall and streams and things like that we had no way of predicting. But you're exactly right. Almost everything you see there by eye, we knew we were going to see. You've clearly seen the whole real. Yeah, those are they're real. They're local high velocity stars. That's a Cat star. So they really racing across. But Gaia has not discovered any new high population stars.
Yes, sir.
So, you also mentioned time domain measurements. Can we hope any type of exoplanet discoveries with all these huge stars?
Yes, is the answer. Yeah, this is the yeah, you can see that in the bottom there's that little arrow pointing across the improvement, more accurate, more complex motions, for example, planets. And so with the extended Gaia mission, there is enough data that one can actually see the little oscillations due to exoplanets. And so the current modelling is that Gaia will produce a complete sample of 70,000 new planetary systems, exoplanetary systems. And for every one of those systems, the mass of the planet will be known, whereas that's not knowable at all now. All you get is the baseline item. But because it's 2D astrometry, Gaia will produce 70,000 planetary systems, all of which will have their mass measured. Not for low-mass Earth-like planets, but for Neptunes and more massive planets than that. But the other rather special feature of those planets is that because Gaia will produce a complete census of every nearby star, right down to the bottom of the black hole sequence. Not only will Gaia tell us which of those systems has planets, but it will also tell us which don't have planets, which is not something we know at all at present. So we'll be able to say what fraction of stars have planets. And then for the relatively nearby ones, Gaia will identify which of the planetary systems which are close enough and with wide enough separation and where in the orbit they are, that those are the ones that can then be imaged by the next generation of large telescopes, extremely large telescope or the James Webb Space Telescope. And so it provides those targets where we should actually be able to look at planets and see them changing as they orbit appearing. So it's going to turn exoplanet science into a science. At present, it's a sort of shopping expedition because people find them in so many different ways.
Thank you. Let's keep further questions for the lunch break. Okay. Now, thank you very much. Our next speaker is Professor Martin Lopez Corredera from the Institute of Astrophysics in Canary Islands. Title of the talk is Kinematics and Dynamics of the Galactic.
Thank you. It's an honor for me to be here presenting my ideas, my point of view about the galaxy. I'm going to talk about mainly about the galactic disk of the Milky Way. As all of you know, we live in a spiral galaxy, in this galaxy, like many others that we have in the nearby universe, including the main galaxy, the local group, which is Andromeda, is also a spiral galaxy. The peculiarity of the Milky Way is that we are embedded in the disk, so we can see only edge on, we cannot see face on. So the separation of the components is not so easy. However, for the Milky Way we have much more information than for the galaxies. We can calculate distance of the stars, so we can provide other kinds of information that are not available for other spiral galaxies. Spiral galaxies are composed of several components. The main one is the disk, precisely. It has a prominent disk, apart from the central components, which is a bulge, possibly a long bar also, or a ring. Also a stellar halo and a dark matter halo is supposed to be there. We will concentrate there, here in the galactic disk, in the disk of the Milky Way. And I will pay attention especially to the outer part, the regions which are farther away from the galactic center. It is now, since many decades ago, that the distribution, the density distribution of the disk is an exponential in the radial direction and also in the vertical direction. This is also known in the Milky Way, for instance, in the work by the Boculers and Pence in 1978. And, for instance, the model of Bacalov-Sonera already includes exponential decrease of the density, the stellar density, in the vertical directions. Previously, at the same time in the 80s, there were other attempts to fit the density distribution in the vertical direction with a square hyperbolic secant, but in the end it was observed that the exponential fit works better. It's more sticky. Near the plane, the distribution is more sticky than the square hyperbolic secant. We also know that indeed there are two disks, as GİLMORE emphasized. One is the thin disk with a scale height of around 300 parsec for the whole population, and we have a thick disk which a much higher scale height, around 1 kiloparsec or a little bit less, and has other peculiarities as the distribution in the alpha enhancement and metallicity is different from the thin disk. So we can distinguish the thick disk observing the stellar distribution or also observing the metallicity distribution. This is something that is also common with other galaxies. Most of the spiral galaxies present a thick disk, as far as we know now. The metallicity is not constant in any of these components, the thin or the thick disk, but there is a gradient in metallicity, both in the radial direction and in the vertical direction. These are some observational facts that we know about the disks. The exponential distribution of the disk is not applicable to all the ranges. For instance, in the inner part of the galaxy, in the central part, usually there is some truncation in the spiral galaxies, which is called type 2 truncation, or holes. This is also a fact in our Milky Way. We know that both in the gas and in the stellar distribution in the plane, the density distribution is not following exactly an exponential, but there is a deficit star of gas in the central regions with respect to the extrapolation of the exponential. However, if we go to the outer part, we don't see any limit of this exponential. We know nowadays that there are these stars at the distance even larger than 25 kiloparsec from the galactic center, and we know they are these stars and not heliostars because they have high metallicity, and they follow more or less an exponential distribution up to these distances. Nonetheless, one has to take into account the flare. The flare, I will explain it later, is that there is a variation of the scale height outwards. There were other works, for instance, Miniti et al. Or Morris et al. That pointed at possible cutoff or a possible decrease of the density with respect to an extrapolation of the exponential, but they have not taken into account the flare. This is the point. If you examine the stars in the plane, you see a deficit of stars, but these stars are moved away from the plane. If you integrate all the planes, all the stars in the vertical direction, you have more or less an exponential distribution. This is also true for the gas. And even we know for the gas that up to a distance of 40 kiloparsec, the exponential distribution fits quite well. With some asymmetries, with some fluctuations, but in general, fits quite well. Lopsidedness is another characteristic of many galaxies. It is believed that around 30% of the galaxies present some distortion of the axisymmetry. Lopsidedness means this, that there is non-axisymmetrical density distribution, especially in the outer parts of the galaxy. We don't know much about this fact, this lopsidedness in the stellar distribution. However, for the gas, it was already observed for distance larger than 20 kiloparsec. The flare, that I mentioned before, consists in a variation of the scale height, the vertical distribution, the exponential distribution of the scale height with the distance. And we know nowadays that there is a flare in gas and in the stellar distribution, both in young and old population. Moreover, there is also a variation of the scale height with azimuth. Here we see in this plot, we see the half width al maximum as a function of the distance, and we see that if we separate the sky in both parts, north and south, there is a variation also. There is an increase with distance, but there is also a difference between north and south, so it depends also on the azimuth, for gas at least. Perhaps one of the most prominent features of the galactic disk, of the outer galactic disk, is the worm. A feature which is well known since more than 60 years ago in the gas. And we recently, in the last 20 years, was also found for the stellar distribution, both for the young stars and old stars. The work consists in that some departure from a flat disk. The disk is not totally flat, but is slightly shifted towards north or towards south, depending on the position, like it is plotted here. And we know that for the Milky Way, in particular, there is a non-symmetric worm. So the amplitude of the worm in the north increase monotonously for the gas. However, for the southern world, there is an increase up to 15 kiloparsec and then a decrease again. Here I show a recent picture published in Nature a few months ago, using surface, in which we also observe the world for the stellar distribution. In any case, there are many analyses, both for the old population and the young population, and both indicate this, the existence of this world. So this is what we know, roughly speaking, about the characteristics, the features of the galactic disk. We know quite a lot about the morphology. About the kinematics, there is not so much information. And the most important information is coming now precisely with the arrival of Gaia. Gaia is perhaps the most important tool in the last years to study the large-scale distribution of the kinematics in the Milky Way. Precisely one day after the data release was made public, one paper was published in Archive. This is the mapping of the Milky Way disk kinematics, which provides quite nice figures of the maps of velocity. Here we can see the three components of the velocity: the radial, this is in cylindrical coordinates, radial, azimuthal, and vertical velocities in the left side, and in the right side is the dispersion of the velocities. The sun is at 8 kiloparsecs, it indicates -8, so it's in the center, and we see that we know all the distribution of the velocities of the stars at distance up to 4 or 5 kiloparsecs from the sun. For these maps, the Gaia collaboration have used all the stars with parallaxes errors lower than 20%. So here the calculation of the distance could be done doing the inversion. The distance is the inverse of the parallax. This can work when the error of the parallax is low enough. If we want to know the distance of the sources for larger errors, we need statistical methods, as GİLMORE emphasizes the previous talk. More recently, we have done some work, an extension of these maps, using also the information of the stars with larger errors, with errors larger than 20%. The fact is that the observed counts of stars as a function of parallax is a convolution of the real distribution of stars with a Gaussian distribution, of the errors. In order to know the real distribution of stars as a function of parallax, we must do a deconvolution, that is an inversion of this integral equation. We have tried different methods, and we concluded that one method, the Lucy's method of inversion, which is an iterative method, works pretty well for these kinds of problems. And once we know the deconvolved distribution of stars, statistically, this cannot be applied for individual stars, it has to be made statistically, we can calculate the average distance of these groups of stars with the formula that I put before. So, certainly it's not as easy to make the inverse of the parallax to recover the distance. We need something more complex. But we can do it. But at least statistically we can recover the average distance of groups of stars. With this new application, we have produced the new maps, the new kinematic maps, extended up to a much higher distance. Now we can reach distance up to 20 kiloparsecs from the galactic center. Here in this map, in the center is the galactic center. The sun is at a distance of 8 kiloparsecs more or less, in the x plus 8. And we can see that we reach distance almost up to 20 kiloparsecs in the anti-center direction. The left part is the same, the radial, the azimuthal, and the vertical velocities. The middle panel is the error of these velocities, and the right panels are the dispersion of velocities. All these data are, by the way, publicly available, so anybody is interested to work with this data, it can be obtained via internet. Here we have another example of plots. In this case, in the x-axis is the direction between the Sun and the galactic center, and the z is the vertical direction. So this is how we will see the maps of velocities in edge-on position for our galaxy in the anti-center direction. We see that there are some regions in which the errors are quite large. In this case, the rest regions in the middle panels, but in any case, for many other places, for many other positions, we can get accurate information, accurate enough to reach a distance up to 20 or 20 and something kiloparsec. And this is important, this extension of the kinematic maps, because precisely the most important features of the outer disk, the flare, the whirl, and others, take place at distance larger than 13 kiloparsec. So with this, we can investigate these interesting regions of the galaxy. Some of the features that we have observed in these maps is an important deviation from zero radial velocities. Zero radial velocities should be obtained on average in case of perfect circular orbits, but we see that the orbits are not circular on average. We see some important deviations, and the radial velocities are between -20 and +20 kilometers per second. There is also an important gradient that we can see, and there are regions of expansion for azimuths larger than -5 degrees, or contraction, that is radial velocities lower than zero, for the rest of the azimuths at distance larger than 10 kiloparsec. We also observe some deviations from zero for the vertical velocities, not as much as the radial velocity, but some vertical velocities between -10 and +10 kilometers per second, with some structure, some large scale structure here. And we obtained the azimuthal velocities for different radii and different azimuths, and for different vertical positions. All this information can be used with many purposes. One of the most important purposes is obtaining the rotation speed of the galaxy. If we apply the Gibbs equation, taking into account the dispersion of velocity, taking into account the correction of the asymmetric drift, we can, from the azimuthal velocities, we can obtain the rotation speed of the galaxy, and not only in the plane, but also in off-plane regions, even 2 or 3 kiloparsec away from the plane. At present, we have obtained that the rotation speed is more or less flat, as we can see, and is not very dependent on the vertical position. It's very negligibly dependent. Within the error bars, it's almost constant. It does not depend too much on the velocity, on the position, the vertical shift. This is more or less in agreement with the rotation speed that we know for the gas also. This is known since many years ago. Okay, so now this is a fast view of kinematics and the morphology of the disk. And now I'm going to talk a brief review of the explanation, dynamical explanations to explain all these facts. First, we may pay attention to the exponential disk, the exponential law in the density distribution. The first ideas that tried to explain this exponential distribution were already more or less 30 or 40 years ago, Stassi, for instance, and they analyzed it in the context of the evolution and the formation of the Milky Way. It was later realized that we need a viscous redistribution of gas to ensure an exponential disk. So the things are not so simple. And in a more recent paper, for instance, Newton 2009, there are other proposals that can produce also a combination of several facts can produce this exponential disk. It says, for instance, the supernova driving galactic outflows, the intrinsic variation in the angular momentum distribution of the halo gas, and the inefficiency of star formation at large radii. When we combine all these aspects, we can reproduce the exponential disk in the radial direction. For the vertical distribution, the discussion comes even for longer time ago. Spitzer, already in the 1942, proposes that we should expect an isothermal distribution for the gas and also for the stellar, assuming both the hypothesis of hydrostatic equilibrium and a Poissonian equation for the density and the gravity. If we combine these two equations, we get the famous square hyperbolic secant equation. I have mentioned before that this is not the case. Our case is that the distribution of stars with the vertical distance is not a square hyperbolic secant, but is closer to exponential distribution, that is steeper in the plane. So some further analysis are necessary to explain why we are not in an isothermal distribution. One proposal was given, for instance, by Barker and Yoshi already in 1986, that proposes that the exponential set profiles are due to that the gaseous protodisk settle into isothermal equilibrium prior to star formation and subsequent gas cooling at a rate comparable to star formation rate. A more simple explanation comes, for instance, from Banerjee and Job, 2007, that they say that simply there are several disks. There is a gas disk and there is a stellar disk, and since the gas disk is much more concentrated than the stellar disk produced, that the stellar distribution is more steeper than the square hyperbolic secant. These are some few ideas that are in the literature. Of course, there are more ideas, but these are some of the most important, perhaps. The existence of the thick disk was also explained in many ways. In general, it is believed that there is due to some heating of the disks, heating in the sense of we increase the dispersion of velocities of the disk for this component, and this can be due to many facts like collision with accreted gas, satellites, radial migration, etc. There is a wide range of possible explanations for the thick disk, for the existence of the thick disk. For the flare, the increase of the scale height outwards, we have to say almost the same thing that we said before. In principle, the isothermal distribution does not work, even if we take into account that the disk is not thin, so we take into account that there is a non-negligible radial acceleration, even taking into account that the flare will be very small, much smaller than observed, so we need something else. The most simple explanation is just the combination of different components of the disk. The component for the gas, molecular and atomic gas, the component of the stars, and also taking into account the dark matter, the halo of the dark matter. When we combine all this, and we make some calculations and simulations, we see that the flare can be produced according to these authors. There are other alternative ideas, for instance, the presence of magnetic fields, by Bataner and Florido, for instance, or the accretion of intergalactic matter onto the disk. This is something, the idea that I have explored, and can produce also flares, increase of the scale height. The lopsidedness was first discovered or first emphasized by Baldwin et al. In the 1980, and they have interpreted this lopsidedness as a constitution of several elliptical orbits in which all the lines of upside rotate at the same rate, like this diagram that I have plotted here. There are, however, many other possible ideas to explain this non-axis symmetry of the disk. For instance, the spontaneous growth of modes, which are long-lived, or the response to a distorted halo. Even there are exotic proposals, like the existence of a possible ring of dark matter in the external disk, or the fact that the disk, the center of the disk and the center of the halo are not perfectly aligned, and this produces these asymmetries. Gas accretion onto the disk is also a possible explanation. Mergers, tidal interaction, etc. For this, there are plenty of possible explanations. For the azimuthal dependence of the scale height, not the radial dependence, which is the flare, but also the azimuthal dependence, it depends on the galactic azimuth. There is one exotic proposal that by Calverla. Calverla are the people that have been using the radio maps, analyzing this asymmetry. So they have proposed that possibly a ring of dark matter embedded in the galactic disk with different, with variation of the thickness of the radius can explain that. However, we have not any proof, there is not any observational support for a ring of dark matter embedded on the disk. A more natural solution, I think, would be simply assuming that there is an accretion of intergalactic matter onto the disk. And this accretion is not polar, it has an angle, on average, has an angle with respect to the galactic disk. And this variation of the angle is what produces different pressures in different positions of the disk, giving different scale heights for different afternoons. The warp. Now I will dedicate some few slides to the warp, which is perhaps one of the most important features in the outer disk. It is well known, the warp, the existence of the warp in our galaxy since the 50s, 60 years ago, and after the discovery, many ideas came to try to explain dynamically why the warp is there. At the beginning, it was thought that in an isolated disk, we could generate warps and this could be kept for a long time. However, the famous paper by Hunter and Tour of 1969 showed that this is not enough because in a short time the warp should be distributed. In more recent years, there have been other works using the bending weight stability, so vertical resonance, produced by the galactic bar, that tries to still keep this idea that the warp can be produced in an isolated disk. However, the warps are usually very small, and it is not clear that the lifetime of this warp is very, very large. And it should be a long time for the warps, because we know that most of the spiral galaxies present warps, and they are not being destroyed frequently. So it's assumed more or less that the warps should be should spend few million years at least. There are some other proposals, for instance, the magnetic fields, the axiom of the halo, a misaligned halo. Perhaps this is the most popular idea nowadays, the misaligned halo, but the axis of the halo is not the same one as the axis of the disk, and this produces a gravitational interaction that is an exchange of angular momentum. Another idea is that there is an accretion directly onto the disk, not in the halo, onto the disk of intergalactic matter, as I said before, that produces this exchange of angular momentum. Let's analyze with more detail these four ideas. The idea of interaction with a satellite, in general, for galaxies, it could work. However, for our galaxy, in particular for Milky Way, we know that there is not enough mass, either in the Magellanic Clouds or the Sagittarius Corpus, there is not enough mass to produce the amplitude of the observed galactic warp. There was a proposal of an amplification of the Magellanic Cloud tides with the interaction of the halo. However, later criticism showed that the position of the warp is not the same that it is observed. So at present, we don't know how to explain with tidal interaction the warp of the Milky Way in these terms. Magnetic fields is an idea, for me it's an interesting idea, although it has not been enough explored. It needs further works. It was proposed in the 90s by Bataner and collaborators, and they assume that there is an intergalactic magnetic field plus a galactic magnetic field, And the gradient of these magnetic fields is what produces this exchange of angular momentum, produces the torque. It is enough with an intergalactic magnetic field of the order of 1 microgauss, which is acceptable as far as we know, to produce these works. However, as I say, these works have been done 20 years ago, and I think they have not been, the community has not paid enough attention to these ideas. The community is more obsessed, in my opinion, with the idea of the dark matter and the halos, and they have neglected this magnetic field ideas. Perhaps the most popular idea, the most extended idea nowadays, is the one proposed by Vinny and collaborators. As I said, that the halo is the axis is misaligned with respect of the axis of the disk, and this produces some gravitational interaction. Nonetheless, there is here some doubt that I have about this hypothesis, that how this misalignment is produced. Some people claim that this is produces in the formation of our galaxy, but it is not clear that it can be maintained, kept for a long time in the galaxy. So the mutual interaction, gravitational interaction, should push the halo to get immediately aligned with the disk. And the other idea is that there is an intergalactic matter accretion into the halo that produces this continuous deviation, this continuous shift of the halo. However, here the problem is how to explain the interaction of the dark matter halo with the intergalactic matter, because as we know, this non-variable dark matter does not interact very weakly with the matter. So we don't know the mechanism how the halo can trap the intergalactic matter. The fourth proposal that I have mentioned before is that the accretion of intergalactic matter is not into the halo, but directly onto the disk. And there is a net transfer of angular momentum because of the inclination of the wave of the accreted matter. If it were polar, the accretion netly will be a zero transfer of angular momentum. But due to the asymmetry, there is some net distribution of angular momentum, so some rings gain angular momentum and other rings lose angular momentum. According to some calculations, it is enough with an infall velocity of around 100 kilometers per second, with a baryon density of 10 to minus 25 kilograms per cubic meter, that gives place to a total accretion in the whole disk of 1 solar mass per year. An accretion of 1 solar mass per year, which is more or less in agreement with other observations in our galaxy, this will be enough to produce the work in our galaxy. Moreover, this hypothesis can explain the existence of the U warps, not only the S warps. The U warps are those with this shape, which are very strange and acquired. They are not very typical. Only 5 or 10% of the galaxies present U warps, most of them present S warps, the H-on. But this mechanism can also explain the U warps, because apart from the transmission of angular momentum, gives also transmission of linear momentum, and this is what is producing the U warp. According to the calculation of the frequency of the S warps and U warps, we see that this hypothesis explains more or less what we observe. And also is in agreement with the fact that the amplitude of the warp depends on the environment. If we compare the idea of the accretion onto the disk with the idea of accretion into the halo, I see here some advantages in this first one. First, as I said, we have no idea how the halo can interact with the intergalactic matter to trap the material. Second, there are some works about the correlation of the dark matter ratio in the rotation curves, analyzing the rotation curves, and the amplitude of the warps, and there is no correlation at all. So this is somewhat against the idea of the importance of the halo. Apparently, the size of the halo has nothing to do with the amplitude of the world. Third, and more important, we observe that the gas is more warped than the stars, especially the all-stars, and in the Milky Way at least. And we observe that the lenticular galaxies have a disk, but they have no gas. Lenticular galaxies are not warped at all. So apparently the gas is necessary to produce this warp. This is in favor of the accretion of onto the disk because of the interaction of gas with gas, and is, I would say, against the idea of purely gravitational interaction, because a purely gravitational interaction between halo and disk should not distinguish between gas and stars. The gravitation is the same for gas and stars. So if we observe some difference for both, means that there is something special in the interaction with the gas. Possibly this accretion. Moreover, there are in the literature plenty of other facts that indicate the necessity of an accretion of intergalactic matter onto the disk. So I think this idea fits very well in many facts and is perhaps one of the favorite candidates to explain, at least in the Milky Way, the existence of the world. But possibly there is a combination of several factors. Now, a few words about the explanation of the kinematics. The kinematics I have shown previously, the kinematic maps, the extended kinematic maps, and we are still working in that. We are now preparing a paper that will be submitted very soon, in 1 or 2 weeks, which are the possible factors that explain these radial gradients and vertical gradients in the large scale structure of the Milky Way. We have seen that, for instance, in the literature there are explanations in terms of the interaction with the spiral arms. The overdensity of the spiral arms can produce some deviations from zero of the radial velocities because of the gravity. The spiral arms pushes or pulls the stars that are near them. If this were true, the zero velocity position in the maps should more or less agree with the position of the spiral arms. If we compare here in these maps the position of the spiral arms and the map of the velocity, in which the white color represents zero velocity and the red color is positive and the blue color is negative, we see some coincidence, perhaps in the inner part, for radius lower than 10 kiloparsecs. Possibly we can admit that the spiral arms has an influence in this part, but definitely the most important feature, which is the gradient of radial velocity for radius larger than 10 kiloparsecs, we see that there is a big change from blue colors to red color in the right-hand side. This does not fit at all with the spiral arm hypothesis, so something else must be taking place there, different from the spiral arms. We have also analyzed the idea of possible radial migration due to tidal streams, the effect of the galactic bar, the mergers, but these are not enough to explain this large-scale feature, a distance between 10 and 20 kiloparsecs from the galactic center. Vertical velocities, however, can be explained with simple facts like minor mergers. We must bear in mind that major mergers are excluded because of other reasons, because of the chemical analysis in our galaxy. So there is no major merger in our galaxy, but there may be some small accretion of satellites or clouds of intergalactic medium that produce this deviation from zero velocities. Also, the effect of the warp can produce some component, some part of the vertical velocity, the flare in the dispersion of velocities. However, in our analysis, we have concluded that perhaps the most important component in the dynamics of the galaxy is to bear in mind that our galaxy is not in equilibrium, especially in the outer part. The outer part, at 15 or 20 kiloparsecs from the galactic center, stars which are in this outer part have, along the life of the galaxy, have very few rotations about the galactic center, so possibly they have no time to reach the equilibrium. And the big orbits are not circular yet. They need longer time to reach this equilibrium. So if we carry out some simulations, here I plot some of them, we can see that it's very easy to see that the non-zero radial velocities are produced because of this fact, also in the vertical component. Finally, a few words about the azimuthal component of the velocity and the rotation speed. Here, I showed you the rotation speed obtained with this Gaia data for stars and different vertical heights. Sorry that the characters are very small, you cannot see here the numbers, but these are different rotation speeds at different heights from the plane, at different distance from the plane. We see the most just looking by eye, the most prominent fact here is that we see it's a flat rotation curve and very small dependent on the vertical distance. This is more in agreement with the existence of a very dominant dark matter halo, and is not very compatible with a month idea. Month, as you know, the modified Newtonian dynamics can explain perfectly well the flat rotation curve in the plane, and is an alternative explanation to the existence of dark matter. However, if we assume month, there should be a decrease, a very significant decrease of the amplitude of the rotation speed with the vertical distance, and we don't see that. Apparently, this fits better with the idea of dark matter. Nonetheless, this is not the final chapter of this discussion about whether month or dark matter is the true hypothesis. And there are many other papers analyzing the kinematics, particularly the dispersion of velocities, which is even more important than the rotation speed itself. And in the literature, there is not a general agreement. For instance, there is a paper, a couple of papers by Moni et al. Of 2012 and 2015, that they claim that the dispersion of velocities is not compatible with the existence of a halo of dark matter. They claim that the lack of dark matter fits better the dispersion of velocities. There are, however, other papers replying to the first one, by Bolometric, by all the other people, that they think that the presence of dark matter is there. So there is not a general agreement as far as I could understand reading the literature. My impression is that we are using some tools like the Jeans equation that requires equilibrium. The Jeans equation requires the assumption of the galaxy to be in equilibrium. And the non-equilibrium effects can be very important. This was emphasized, for instance, in a recent paper by Hight et al. This year. So possibly the difference between the conclusions of different authors can stem from the application of the Jeans equation, which is not exact, accurate enough in a non-equilibrium case. Even our rotation speed that we have in these plots uses the Jeans equation to correct from the asymmetric drifts, but we have not taken yet into account the non-equilibrium. So possibly the discussion can extend from there. Yes, well, this was more or less all the collection of many ideas. It was a brief review. I have not mentioned all the ideas because there are many more, but just few ideas related with the morphology, the kinematics, and the dynamics of the Milky Way, of the disk. And now I will make a summary of perhaps the 4 or 5 more important ideas. There are many more, but the 5 more important ideas are the following. For instance, the gravitational interaction with a satellite is an important idea that explains at least 4 facts of our list of features. Explains the lopsidedness, explains the radial and the vertical velocities that we have observed that are different from zero, and explains the existence of the physics Minor mergers explain the same thing, the same observations. A non-axisymmetrical component like the galactic bar or spiral arms or a ring of dark matter, if we try to look for exotic proposals, can explain also some of the observed features. For instance, the variation of the scale height with the azimuth can explain also the radial velocities or the truncation in the inner disk. My favorite explanation, however, and this is a particular point of view, is my opinion, of course anybody can have other opinions, is that the accretion of intergalactic matter onto the disk explains most of the things that we have been observing in the morphology and the kinematics of the disk. Explains the thick disk, explains the lopsidedness, the vertical velocities, the flares, the variation of the scale height with the azimuth, the S-words, the U-words, and many other facts that have nothing to do with the morphology or kinematics, but have to do with the chemical evolution or the formation of some components. The non-equilibrium, in our opinion, in my opinion, is also an important component. At least, if we are going to analyze the galactic disk at large distance from the galactic center, a distance over 15 kiloparsec, I think the non-equilibrium is something to take into account. And it explains, in general, the lopsidedness. It explains all the features that we have seen in the kinematic maps of Gaia, the stainless kinematic map of Gaia. This is the final slide, in which I summarize my conclusions. The Milky Way disk, especially in the outer part, presents many features useful to test ideas on galactic dynamics. There are, however, many hypotheses to explain the same facts, so it's not easy to know which one is correct. Possibly more than one of the hypotheses applies at the same time. Possibly we are combining different effects to produce the same observation. And if I have to choose, as I say, it's my personal point of view, it's not the absolute truth, but if I have to choose an image of the Milky Way just to explain all this fact, I would say that the formation of this with several components, the stars, the gas, the molecular gas, the atomic gas, the dark matter also, together with this, taking into account the star formation efficiency, the accretion of intergalactic matter onto the disk, and the non-equilibrium, all these things combined can explain almost everything that we know about the Milky Way. There are alternatives, of course, but this at least is one powerful explanation. And this is all that I have to offer you. Thank you again for your attention.
Thank you very much. Any question or comment? Kürşat? Would you pass the mic?
Thank you. It was a very nice talk. I would like to ask one question about these flares. These are similar with this galactic quantum model that the gas comes from the disk after a supernova explosion and comes back to the disk. These are similar with the flares, or the source of the flares are different? Because I know that...
No, it has nothing to do with the solar flares.
No, not solar, but galactic quantum model.
Galactic quantum, no, but even if the word reminds to these flares, also this ejection, no, the flare is the name that is given to the thickness of the galactic disk is increasing with distance. This is only that.
Because when you say about this one solar mass per year accretion from the intergalactic medium, actually the galactic quantum model can create much more. I mean, if it's the limits, then it will be more mass will come, and then what will happen?
This is the number that I have given to explain the amplitude of the world. According to some calculations, an accretion of one solar mass per year is enough to explain the amplitude of the world. And this is more or less, as far as I know, with other problems. There is the problem of the GİLMORE problem, all these many problems of chemical evolution in the galaxy. Calculate an order of magnitude of one solar mass. Can be the mechanism is not clear. Can be some loop, like you say, that is ejection and then attraction again, or simply that we have the intergalactic medium filled with some material, and since the galaxy, the Milky Way, is moving with respect to this intergalactic medium, is accreting, is sweeping all the material that is
yeah, or it can be both. And I would like to also contribute one more thing. You said you don't see anything to this kind of thing in the lens to the galaxies, but I see that. I know some guys reach early-time galaxies and warps and all these effects. So, and we are...
you see, lenticular galaxy, the mean?
Yes.
What kind of data you use?
I'm using, actually, I will show tomorrow some of them, but yeah, we have these gas-rich early-time galaxies that observed in Atlas 3D project, and we have warps and some,
Yeah,
you know...
possibly. No, if you have gas, possibly you have warps.
Yeah.
My point is that in the disk where there is no gas, for example, in the class, in most of the lenticular galaxies where there is no gas, there is only stellar component. They are almost lenticular is something in between elliptical and this galaxy and spiral galaxy. So it's just the point in which they start to produce gas. If there is no gas, there is no warp. It's not my paper. It is a paper by Sanchez Saavedra et al. 2003, and they have concluded in their analysis that all lenticular galaxies should not have warp. Possibly there are more recent data that show something. Thank you.
Okay, thank you very much. Let me remind you that we will take a meeting photograph before the lunch at the stairs. And the last talk is last talk before noon. Is a short talk coming by Tenay SAGUNER RAMPALDİ. Title of the talk is Small Telescopes Can Also Do Great Galactic Science. And please keep it 7 minutes.
Today I am going to speak about a project that I followed during my PhD thesis, and I wanted to present this talk with small telescopes can also do great galactic science, to encourage the young researchers to use small telescopes to participate in the galactic studies or the follow-up observations. Well, the small telescope that I am going to speak about is a 1.22 meter Asiago telescope, which I carried this observational project during the PhD time. It is a very old telescope. It built in 1942. Now the telescope is not like this, but when I used it, it was very old-fashioned. Now everything is automatic. You can observe with this telescope from your home. We wanted to see how good we can obtain spectroscopic data to do some galactic studies, to study the metallicity gradient of the disk and the space velocity distribution of the moving groups, streams, and other overdensity regions. So we selected the red clump stars because they are bright. They have a very instinct brightness. They are giants, and we select 500 of them from the Hipparcos catalog because Gaia was still to go on, and we selected a very good sample, avoiding the extinction in the galactic plane, and we observed them with 1.22 telescope. We use a very standard spectroscopic instrument. It was a medium resolution long slit spectrograph with a resolving power 5500, but we obtain a very high signal to noise spectra. At the end of the 2 years that we go on with the observations, we observed over 400 stars from the selection, let's say, and we perform a lot of tests to see how good and how we can go further to obtain a better results. And at the end, this is our wavelength range that we observed from 4,800 till 6,000 angstrom, and we obtain the radial velocities for these stars using the standard IRAF FX score, which is making a cross correlation between the observed spectra and the template spectra that you can choose in between a synthetic spectra and a real observed spectra. For our purpose, we try to observe the radial velocity standard stars each night, at least 3 of them, and use them as templates for the radial velocity determination. Here you can see we selected 15 radial velocity standard stars from UAU catalog, which are having the same spectral type and close to the objects that we are observing. So here you can see the mean difference between the tabular values and the values that we derive from FX score, from the cross correlation. So this plot is presenting the mean velocities that we calculated for these 15 stars during the 2 years' time. And then for atmospheric parameters, we use chi-square techniques. We develop interface to calculate the temperature, the gravity, and the metallicity of the stars that we observe. And we use synthetic spectral libraries for the chi-square technique. And here you can see, well, it is a old-fashioned now. Maybe we can do better. But you can select the spectral library that you want to use according to the metallicity, and the program is doing everything by itself, by calculating the minimum chi-square of convolution between the synthetic spectra and the observed one, and it is giving the astrophysical parameters for the stars. Well, I am not going to speak about the applications, but I just wanted to show the accuracy that you can achieve with a small telescope. Here you can see the comparison of 3 similar works that has done with high-resolution spectrographs and bigger telescopes for the common stars that we observe and was presented in those catalogs. So you can see for the temperature, you can see for the log G, the gravity, and then you can see for the metallicity, the overall metallicity of the observed stars and the derived values. So according to those results, we can say that we can have 88 Kelvin difference for the temperatures, so 0.38 dex of the log G and 0.17 for the metallicity, the accuracy we achieve at the end. Well, we put them together in a catalog that that can be used to perform some galactic studies. At the beginning, we thought that to see how good we can see the gradients, the overdensity regions. So this is the overall catalog. We are looking at 520 stars here in the galactic coordinates, and here I put a Mexican hat over the density plot to show you that even with the 520 stars, we are able to see the over density regions called the streams and the moving groups like Pleiades, Hercules in our sample. And of course, now there is the Gaia satellite taking data, and after the data release 2, we want to confirm and see how good was the observations in the framework of the Gaia. So here I put a plot for the observed stars. Right here you can, in the first plot you see for 242 stars, because I just use the highest quality flag of the Gaia data that were common for the stars, and the second one is for the second epoch of observations that we performed. So for the radial velocities between the DR2 data release and the arcs, we have 1.88 kilometer per second of difference, mean difference. And well, there are two stars that I didn't take them out because in the Gaia data they were having still a good quality of the derived radial velocity parameter, but it has to be checked because in the second plot with 60 stars that were common in the second epoch of observations, the mean difference between the Gaia and the arcs is 0.42 with a sigma 4.88. And well, there is also the temperature available in the DR2 release, so we want to check also for this. Well, the scattering is a little bit worse, let's say, from the radial velocities, but it is because probably, now we have to check it, but the different approach that arcs and Gaia took for the determination of the temperature for the observed stars. So that's all. Thank you very much.
Thank you very much. Keep questions and okay, let's take questions.
How is the comparison of your catalog with the apogee for red clams? There's a special catalog of red clams with apogee.
And I didn't do that. I have to. Now we are checking and let's say going on, because we were just curious to see how good, and we saw that we are very good in comparison with the Gaia data, and we decided to go further and check and maybe publish a validation report on that work. So this is something that I will do.
Timur?
If I'm not wrong, so the lowest metallicity model that you have in the grid for chi-square determination of model parameters was minus 1.5, right?
No, we took the solar metallicity.
No,
basically.
you have grid of models, right? It's actually probably first or second slide that shows us. Yes, you have models were listed, grid of models, and the lowest metallicity was minus 1.5.
And here.
No. In the code view, there was actually
okay. This. No.
One more
previous slide at the very beginning.
Okay.
This, okay?
So what I see is here actually minus 1.5, right? This is the lowest metal state grid that you have in your model.
Yes.
Okay. So if we are actually measuring Gaia radial velocities, right? Or if you are looking at Gaia radial velocities, at this metals regime, it's very difficult to find Gaia template, reliable Gaia template with certain temperature and gravity, if I'm not wrong. So can you elaborate on this? How did you actually take this into consideration, or for all your own clusters, you had excellent Gaia templates at this low metal states?
George, is it hard to find such template in Gaia?
The metal states of these stars haven't been measured yet. So I think the DR2 main attribute parameter was the effective temperature. So yeah, so I think so this will come in DR3. But yeah, so it is difficult to get the right template now.
Thanks. Okay. Thank you very much. Let's take a photograph and have a lunch.
Buradayız efendim hepimiz. Evet. Fark edeceğiz. Buradayız hep beraber hocam.
We've been collaborating and been in email contact with for the last 9 years, and so it's actually fantastic to meet these people in person. Thank you very much for your hospitality. So I'm going to really pick up the mantle, carry on to pick up the baton. So I'm mixing my metaphors now. Picking up the baton from Jerry's talk earlier this morning. So Jerry gave an excellent overview of the science of Gaia. And so I'm going to, and he mentioned that the data from Gaia is all science ready, and there's a lot of people are working behind the scenes to make that, make the data science ready. And I'm one of those people, and so I'll give you a bit of an insight into that, and talk you through the data. So as Jerry said, the more data you get, especially with Gaia, the more complex it is, and so the more things you need to know in order to optimally use that data. And so I'll take you through a few of the less obvious parts of the data with the radio velocity spectrometer, RVS for short. And this is me in Gaia. So this picture here at Gaia's launch. So Gaia's in space. They're a few minutes after launch back in 2013. And that's my silhouette. It's the closest I got to actually seeing the satellite in reality. So what I'd like to present to you today is I'll talk you through a few aspects of the RVS instrument, and I'll talk to you about my institute, the Mars Space Science Laboratory's contribution to the RVS hardware and software, and then talk to you about the RVS data itself. So this is a picture from the web, which you may have seen already. So you've seen pictures of Gaia from the outside. So this is from the inside when it was being built. So we've got the back of one of the primary mirrors closest to us, and then the side of it a bit further around. And they're both mounted on the optical bench here. There's a tertiary mirror down there, and then the CCDs and the focal plane are hidden away in this blue part down here. So the radio velocity spectrometer is this box here. So zooming in a bit. So here it is. So we've got the last couple of mirrors, M5 and M6, before the light hits the focal plane. So as Jerry's movie that showed earlier, Gaia is continually spinning, and so the sky drifts across the focal plane. So initially, it drifts across the focal plane unimpeded, so Gaia's just seeing the white light from the stars. But then, as the drift continues, the line of sight of that drift is interrupted by the radio velocity spectrometer in this box here. And its dimensions and its weight, just for interest. And then inside that box, you've got various optical elements. So it's a silicon carbide structure with thermal properties, and it's got these brackets and these little bipods
So this was the most delicate part of the RBS construction, was making sure that these bipods would be able to withstand the vibration of the ball. And so we've got our bandpass filter at the front here, and then take a view from the side. There's the bandpass filter at the front again. And then we've got these got various spherical surfaces. So this is because the radial velocity spectrometer is off axis, so it's not in the centre of the field of view of Gaia. And so there's all these aberrations which need to be corrected by these spherical surfaces here. So this is just showing you the curvature on one of these lenses. And they also flat surfaces in there as well. So there's 6 optical elements in total with the transmission grating in the middle. That's a picture of the transmission grating separated out from the rest of the instrument. So all of these complex optics are within this box, and the rainbow cartoon there is illustrating the light that is dispersed onto the CCDs, as you saw in Gerard's movie. And here's a zoom in on the focal plane, again a bit like Gerard's movie. So the Gaia's entire field of view stretches across nearly 0.7 of a degree. That gives you, and then over the normal 5-year mission, we've got 70 transits of every source. So the RBS field of view is that little bit shorter, so it's 12 CCDs over 4 of the rows of Gaia, whereas Gaia's got a total of 7. So that means this field of view is smaller, and hence the average number of transits that the radial velocity spectrometer sees over the course of the normal 5 years is fewer, and it's about 42. So in terms of how we've contributed to the radial velocity spectrometer's hardware and software. So here's our lab in the Surrey countryside, as I mentioned. So I showed this picture partly because it's nice, but partly also to encourage visits between our institutions. And we've already been talking about how we might achieve this over lunch. And so we would welcome visits from any of you to come to our lab here. So here's the MSSL Gaia team with. And these, incidentally, these are the clothes that are in my suitcase that I'm wearing there that I meant to wear today, but unfortunately couldn't. So here's the team, and they're mainly software engineers, and I'm the Gaia scientist, along with Professor Mark Roper, who's in the middle holding the award, and he was instrumental in the Mars Space Science Laboratory's role in Gaia. So he led the RBS instrument concept development back in the early 2000s, and provided scientific and technical support to Ashton, who built the RBS. And then through his role there, MSSL won a contract to test all of the more than 106 Gaia CCDs. So this was quite an enormous testing program. The photograph here shows the jig with a vacuum chamber with the top pulled up. Four Gaias, actually so only one in position in the picture, but 4 locations where they've been tested. So all these CCDs were put through a vigorous testing program pre-launch, and testing all 106 took 6 years actually between 2006 and 2012. So all the hardware part of Gaia is obviously finished, because Gaia's been in orbit for 5 years now. But the ongoing part is the software. So the past 13 years, MSSL has been a major part of the team in Europe. Has been developing the software to process the RBS data, and it's part of the coordination unit CU6, as part of Gaia's data processing and analysis consortium. So this is a picture of the CU6 family. So these are the people to thank when you use the radial velocities for your science. So as Jerry said, there's and this is just one part of the team behind all the Gaia data. There's 9 CUs in total that contribute to getting the data science ready for you guys to use. So then just a brief word about the software. I won't talk too much about this, just to say that it's quite a lot of processing to be done, and all the software is written by professional software software engineers. So the data obviously requires calibration and extraction, and then selection of the correct template with which to cross-correlate spectra and to actually provide the radio velocities. So just to give you an idea about what I do on a day-to-day basis and SSL's role in the code, the boxes overlaid here give an idea of our contribution to the code. So as you can see, we're largely responsible for the calibration of the radio velocities spectrometer, and also the extraction and the multiple transit analysis, which I'll come back to later. So all of these details are in the paper mentioned there. So in terms of actually what the processing needs to do, so Gaia's second data release back in April 2018, we processed 280 million RBS spectra, brighter than the GRBS magnitude of 12. So to give you an idea of, so this is an unpublished magnitude. So the relationship with the published magnitude G is given here. So the difference is about 0.65 for an unread and G2B star, like the sun. Of course, this is a color-dependent relationship. And so the pipeline processed all these 280 million spectra. Had to deal with problems like bias non-uniformity, which is shown in the bottom left now. We have artificial steps in the spectra, which is a feature fairly unique to the way Gaia operates the CCDs, due to the fact that it's spinning. And so all of these steps and the Schway-like background and everything needs to be calibrated. And so the calibration, the resulting calibration is shown on the right-hand side here. So this is a typical star at about G of 11th magnitude. So you can see the calcium lines in there, but you can't really see many other lines. But still, this is pretty good for 4.4 second exposure, which is the amount of time that this star's been exposed for to get that spectrum. So to orientate yourself a bit better, in terms of the lines available in the spectrum, the plot above shows a much brighter star, showing the calcium lines, but also iron and silicon and metals besides. So onto the data itself and what's available. So I'll go through the radio velocity data that's currently publicly available in DR2, and then I'll also talk about what our plans are for the early data release 3 and full data release 3 in the coming months. And I'll also finish talking about RBS data in the Gaia photometric fields. So onto DR2 and then the data that many of you have already played with, and certainly Martin has, as he showed earlier, played with this data to great effect. So the content here, just 6 numbers is what was provided in the radio velocity in the radio velocity part of DR2. So I'll go through each in turn to illustrate their properties. So the first plot here on the top left is showing the G magnitude of all the stars with radio velocities in DR2. So you can see that it's not a sharp cutoff in G. So it's partly because of the colour difference between G and GRBS, and also because of the GRBS itself was defined from ground-based catalogues, most of which have problems of their own. So the next catalogue will be selected purely from Gaia data, which will give a much sharper cutoff in GRBS and a more characteristic shape in G. So top right plot shows the number density of stars in galactic coordinates. So you can see we're very much dominated in terms of numbers towards the galactic plane. The bottom right plot is the completeness. So less completeness being blue and more completeness being red. So you can also see, although most of our stars are in the galactic plane, this is also where our greatest completeness lies. And this is an issue that we'll be trying to improve in the next data weeks, but I'll come back to that later. The bottom left plot shows the completeness of stars in the Gaia catalogue that have a radial velocity as a function of G magnitude. you see we're reaching 80% at a G of 12, and then dropping off quite sharply after that, but still having stars with radial velocities right on G of 15. So this is what I was talking about a selection function of the stars that have radial velocities will improve a lot in the next section. So the radial velocity distribution itself. So we're all familiar with this picture. Wonderful all-color, all-sky color map from Gaia DR2 using the BP and RP colors. So here's the so in the same coordinates. Here's the first ever all-sky radial velocity map. So previously to Gaia, radial velocities were generally measured on the ground, and so were necessarily limited by their hemispheric view. But this is the first time that an all-sky radial velocity survey has been conducted, and so this is the first time we've seen such a map without the different systematics of different instruments. So you can see the characteristic pattern of the Or's constants. So this is a histogram of the radial velocities in Gaia DR2. So there's 7.2 million stars in total. So as Martin mentioned, the various demonstration papers use fewer stars than this. The demonstration paper with kinematic maps that was done within the collaboration used about 4 million because some of these stars have a relative parallax uncertainty of more than 20%. But Martin was able to take into account these parallax uncertainties and extend that kinematic mapping, which is we heard about this morning. So using much more of the 7 million stars that are available. So it's interesting actually that we only just beat LAMOST, DR4 actually, in stars with radial velocities got 6.9 million. Although, so next time round we're looking at probably getting 30 million stars. So we will, in terms of numbers, start playing away from the opposition. So the distribution here is on a log scale on the y-axis, so the number of stars against the actual measured line of sight radial velocity. So there's a few features here. There's the tiny bump of large Magellanic cloud stars there. There's the spike there, which I got extremely excited about when I first saw, thinking I found myself a tidal stream, until I realised it's actually the globular cluster NGC 3201, which is on quite a radial orbit, and so appears, and so the radial velocities are measuring that orbit, and so it appears quite strongly in this plot here. So, see, there's a lot of scientific interest in high velocity stars, and in particular, I'm plotting out one high velocity star here, which turned out to be quite controversial. So, didn't really saw this paper. This was lessons from the curious case of the fastest star in Gaia DR2. So this was a star which had a radial velocity in the catalogue of minus 614 kilometers per second, which on its own is enough to classify it as one of the fastest stars. A high velocity star are of great scientific interest to the community, except in collaboration with the people here, we measured the ground-based radial velocity and found it was quite different. So I was at about minus 60 kilometers per second. And so we worked out that this difference comes from chance alignments of stars close together, a bit like illustrated in the sky bomb here, declination against right ascension. The star in question that had this erroneously large negative radial velocities in the square, and another star extremely close with the triangle. And the Gaia scans are shown in orange here. And so we thought we'd been able to do us powerful with these examples when we published the radial velocities in Gaia second data release. But it turns out that chance alignments like this can actually mean that the star with the triangle is actually contaminating the flux that we measure for the star in the square. So this is all to do with the complex window geometry of how the radio velocity spectrometer actually acquires the data and reads it out. So I won't go into the gory details of that. If you'd like to see more about that, it's explained in the paper. But suffice to say that this is a known issue with the data, and there's a website that collects known issues with Gaia's second data release. So this is, I think, quite a natural thing. So the pressure is to publish the Gaia data as soon as we possibly can, and get the community doing science with it. And so this is a case of useful community feedback to show that actually we've got a few things wrong here that we need to correct. So this will so this is a warning that there is this list of 70,000 sources with potentially contaminated radio velocities do exist within Gaia's second data release. So that's about 1% of the total. So that's just something to be aware of if you're looking at this data. So this is the distribution of those stars. So the blue list of 70,000 is now plotted in blue. You see the list actually gets rid of quite a lot of the extremes of the distribution. So most of the extremes are either end, both tails.
Attached to Gaia, and it looks like there are many things to do science in future for young astronomers and young scientists. Now, let's have if there are some questions. Thank you. Yes.
Thank you for nice information. In your radio velocity map of galaxy, where we have a red bulge here and two blue bulge here and something between blues. Is it completely in line with our understanding of the present picture of galaxy? And what does it tell us something new? I mean, this one.
So this particular map isn't really telling us anything new in effect. So it's only to the naked eye. So this is really illustrating quartz constants. So the fact that the radio velocity as a function of galactic longitude is a function of sine 2L. And so this is really showing us that the galaxy isn't rotating as a solid body, but there's a shearing motion in there, effectively. So
these two blobs, like one there, there's something in between. Is it something wrong?
yeah, so no, I think this is in line with our. I think, broadly speaking, it's in line with our expectation. I mean, but I think maybe if you look into the details, then you may find. There's something else, but as far as I know, it's broadly as we expected.
I mean, we usually teach that our galaxy contains hundreds of stars and so on. This Gaia maps or Gaia data, did it help or quantify this number better, or is there any global?
In terms of the total number of stars in the galaxy, I believe it has, and I think the numbers have been revised upwards. I think we're talking sort of 400 billion, is that right? I'm looking at Joe, he's nodding. Yeah. So I think, I'm not, I don't know, I'm not particularly familiar with the word, but that's the word in the Gaia corridors.
Increase. Number is increasing.
Yeah. Yeah. I mean, effectively, Gaia is doing
Timur.
an all-sky survey of the sky with nearly Hubble resolution. So we're going to see more stars than we expected.
Yes, please.
Can you give some further information on diffuse interstellar band identification, especially which kind of templates you are planning to use, because their intensities will be mostly depend on in which direction the star is observed.
So that's a good point. Yes, don't think there were any in the example I showed. No.
And how we see it. Let's move on. Okay. Where does this Galactic Candy project comes from? It is part of a larger project actually, which was awarded by our by Turkish nation. Turkish Scientific and Technological Research Council as of March 2019. The project called was Kinematic Investigation and Mapping of the Solar Vicinity. So its shorter version is KMAP, not KIMAP, as you would expect it. It's because KMAP means, also KMAP means move towards, appear, become available, happen, which is also our motto as a young scientists, because we are a young group, young researchers we have, just fresh postdocs, lots of graduate students, which you will see momentarily. So what will we do with KMAP project? The aim of the KMAP project is to investigate the static and time-dependent kinematic structure of the solar vicinity and to examine the effects of the large-scale perturbation sources on galactic orbits and construct kinematic maps, multidimensional kinematic maps, which is also the hottest topic of the galactic research. So we will take our chances with our data sets and our scientific approaches. We will see if we can make an influence in the literature in 3 years. So, KMAP is a 1001 project, not a 1001 Nights Tale told by Scheherazade, but it's a tale made out of real scientific data by our, as I said, either young in spirit or in physically shape researchers. This is a team with a twist on it. Okay. So, here we go. Let's add some starch on this presentation. Let's add some science on this presentation. So, what is the concept of the candy? Candy stands for, as you might have guessed, chemistry and dynamics of the solar vicinity. In this sub-project, we will use survey data, surveys like astrometric, photometric, and spectroscopic surveys, of course. They are the astrometric part will purely come from the Gaia, and the spectroscopic part comes from high resolution and mid-resolution spectral surveys. We will investigate stars with different luminosity classes and stars in different spectral types. We will do this investigation by using their chemistry, kinematic and dynamic properties, and if we can come up with better ideas and better solutions, we will try to calculate their ages with little errors less than at least 1 gigayear, which is the literature's limit, by the way. We will also use advanced statistical modeling and machine learning algorithms. We have the proper sub-studies, how we can employ these ideas on the data. So, let's move on. Okay. As you see here, one tiny sheet. How galaxies formed in general and how our galaxies formed specifically is still an unsolved question in the astrophysics. We have ideas, we have good solutions, but we don't have a clear picture yet. What we must do? We must do to understand the formation mechanisms, how all these material evolved in time. If we do that, we might put constraints on simulations, and to do so, To do so, we need chemical information of various tracer objects, as you see in this HR diagram of stars and variable stars, and open and globular clusters, and H2 regions. These are proper tracer objects we should use in our studies. Which one to use is up to us, of course, what we want to do, what we want to look for. Of course, these objects should change in a large distance scale. Either you can use current positions in the galaxy, or you can use their orbital positions, or for example, mean galactocentric or distance is also a good choice. Or you may use their guiding radius, so that you can assume that their orbits are circle, and you can calculate it thoroughly there. So, what else? Okay, let's move on a bit more introduction, and we'll do some other stuff. Galaxies are dynamically active ensembles of gas, dust, and stars. And it takes eons to shape their almost stationary appearances. You see? They have been through a lot. Likewise, our galaxy Milky Way has been and still is under the influence of these inner and outer perturbations. So, we have to investigate what do these sources affect our galaxy. Our galaxy, Milky Way, is generally considered to have distinct components, such as bulge at the center, and the disk, and the halo, and each of which have distinct age, chemistry, and kinematics. However, it's not that simple, actually. As you see, there are bubbles, warps, fountains, interactions with satellite galaxies, and also there are inner structures like spiral arms, bar, moving groups, stellar streams, infalling gas and stars. And there's also a supermassive black hole at the center, and there's a nucleus which causes lots of problems in the galaxy. So we have to consider them all. But how? Studies show that these components are not so different, are not so distinct from each other, actually. Even though there are modes of certain chemistry, age, and kinematic behaviors, there is also overlapping regions in metallicity, which also can be seen in this figure. You will see, sorry, the laser pointer is not working. You see thin disk with dashed line and thick disk with dot dashed line and halo with dotted line, and you see their metallicity are overlapping. And this, how can we overcome this problem, was another question, but so far, with the help of the spectroscopic surveys, we found a way to at least separate galactic components on metallicity versus alpha abundances plane. This is one of our upcoming studies of Plane et al. And we used apogee data and tried to separate thin and thick disk components using advanced algorithms such as Gaussian mixture model. We applied it here, and we found the boundary decision line. So yes, they are distinct, but they have overlaps. But if we largen our parameter space, we might be able to separate components using advanced statistics. So let's move on. This is another show of the kinematic overlaps of distinct galactic components. Okay, let's move on. So, I'll take some help from here. Regardless of the transition between these galactic components, they are formed from each other, either in the form of gas clouds or in dark matter halos. And these components are thought to be shaped by an ongoing collapse into a plane of the gas material or by part of stellar evolution of its subjects, and or by merger events with the surrounding environment, such as dwarf galaxies or intergalactic gas clouds. We don't know. Our galaxy is big enough to attract them all. So, however, all this process is governed by gas, initial gas. This gas component affects two ways, actually. Affects in two ways. One is the amount of it at the beginning and how it formed into other materials like stars. And second of it is how the stellar evolution affected this gas along its long time to infall on the galactic plane or towards the bulge, maybe we should say that, like that. So, if we can consider all these ideas during our research, I think it will be a more logical way to approach the problems, to me. Okay. So, you see two major models of how our galaxy is formed in here. One is proposed by Özgecan and Sandwich in 1962, monolithic collapse model. Even though they proposed the rate of collapse very fast, still it's the most basic event that occurred along with others, which is also proposed by Gerard and Zeki in 1978, and it's called hierarchical formation of the galaxy. In this model, they propose that there are little dark matter halos and they collapsed slowly, and at the end, the galaxy is formed, basically, but of course, there are very important details if you want to know more about it. So,
the improvements in the 20th century, not linear but exponential. And now, later on, the code says it is not continuous, but there are jumps in improving science. And we are living in big jump these days. Perhaps astronomers has data, maybe decades, perhaps half a century to work on, still enough. But still, the most important, today we learned how much improvements in the galactic astronomy, but still the basic physics, basic astronomy is important. I talk about here the detached double-line eclipsing binaries. These are special kind of binary stars that, as special class of binary stars, we can get the most accurate parameters of fundamental parameters of stars observations. This is needed directly from, this is needed, why they are needed? Because these accurate parameters are needed for testing testing stellar structure and evolution models. Not only stellar astrophysics, these fundamental parameters, not only important for stellar astrophysics, but also galactic astrophysics, very important. Because stars are the main ingredients of the galaxies. More than 95% of the visible mass is contained within the stars. And you cannot study the evolution of galaxy without knowing the evolution of stars. Fundamental relations. Here, mass-luminosity relation, main-sequence mass-luminosity relation, is discovered empirically by Herstrom and Russell, Adams, and Joy in the first half of the 20th century independently, and updated and improved many times. Mass-radius relation comes after 1950s, the same that defined, calibrated many times, again and again. Mass temperature relation, we don't see any mass temperature relation in the history. Why we don't have that? Because once you have mass luminosity relation and mass radius relation, you don't need mass temperature relation. Because Stefan Boltzmann law, you can get from M to mass of a star, you can get mass of a star from luminosity, then we can get the radius. Once you have luminosity and radius, you can use Stefan Boltzmann law and calculate the temperature. Here, why we need mass luminosity relations? Testing absolute brightness or trigonometric parallaxes. Especially this was important before Hipparcos, before Gaia. Once we try to measure the parallax of the stars from the ground base, especially accepting binaries, radial velocity curve. This is important because once you have this stars gives us absolute magnitude of the stars. Once you have absolute magnitude, you can calculate similar absolute magnitude from the parallax. You can compare, either test one of them. Mass luminosity relation is needed in galactic studies very much. Luminosity functions. To calculate the luminosity functions, you need mass luminosity relations. Initial mass function. And luminous mass of the galaxies, calculated from mass luminosity relations. If dynamic mass available, and this is the virial mass, so the difference between luminous mass and virial mass is the dark matter. Even for calculating dark matter, you need mass luminosity relation. Estimating mass of single stars is important. You know, single stars, only binaries can calculate. Kepler law used on binaries or multiple stars. Single stars doesn't work. So to calculate, to estimate mass of single stars, mass luminosity relation is very useful tool. But here, how can we calculate? Needs to be distance, parallax, and visual magnitude. But here, the critical is the critical. No. Okay. But important is the critical is the bolometric correction. Here, the stars, like black bodies, radiated all wavelengths. And how the energy is distributed to all these wavelengths, and astronomers created photometric filters, different photometric systems. You can see here, in the middle is the sun, how its energy distributed in the wavelength, and hotter star Vega in the blue, and cold star in the right side. But we have a filter, visual filter, only see the middle, just one part. Short wavelength part, high wavelength part, we cannot see. So to observe the brightness, all wavelengths, how can we do that? This comes into the bolometric correction. The definition of bolometric correction is the difference between absolute magnitude, absolute bolometric magnitude, and absolute visual magnitude. And it is the same true for visual bolometric magnitude and visual apparent bolometric magnitude difference, apparent visual magnitude. difference, it works. So what does it mean? The bolometric correction is correction for missing flux, luminosity. Because we don't see just a single filter, we see just one part of the spectrum, there are missing parts. So what is this missing flux, or what is this missing luminosity part? Here, the definition of visual magnitude in any wavelength, just there is a zero, this Q there is a zero constant. You know, if you know, for example, vega, m lambda is 0. If you know the flux above the atmosphere, Q there, to make this m 0. It's a zero point constant. And this can be solved for f lambda, so you can get the flux above the Earth's atmosphere. This is flux coming from the star, from the Earth's atmosphere, actually is ratio of surface flux over the distance. This is the inverse square law. You know, and the distance twice or flux decrease 4 times. Here the definition of bolometric, just only magnitude. There is just certain wavelength. Here is just the bolometric. It is, we can say that we can write the same equation for that, and same equation again. When we divide them side by side, you can get f lambda divided by f bolometric. So it means luminosity of the star certain wavelength divided by total luminosity. Our aim is to get the total luminosity of the star from just single filter measurements. Although it's impossible to measure brightness of all wavelengths, you know, there is no instrument, there is no telescope to see all wavelengths. Telescopes are limited to see certain wavelengths. There are X-ray telescopes, there are ultraviolet telescopes. We cannot see. There is no detector. Detectors are also limited. But how can we get the brightness of the star for all wavelengths? This comes from, we need to get from the bolometric correction. You know, if you know the bolometric correction, observe the star in visual apparent magnitude, just adding that, you can get the bolometric. You can get real luminosity of the star. Now, problem is how bolometric corrections are calculated. Here, again, detached double line eclipsing binaries comes to the role again. Or stars with accurately known radii and effective temperatures. It is the definition of bolometric correction, difference in bolometric absolute magnitude minus visual absolute magnitude. Here, absolute bolometric magnitudes comes from comparing to the sun. Here, what you need, only 2 parameters are needed. Radius of the star with respect to sun, and temperature of the star with respect to sun. So the first M-ball bolometric magnitude, absolute magnitude, can be calculated easily. Absolute visual magnitude comes from, also formula again, visual apparent brightness comes from observations directly. And there the distance comes from the parallaxes, and what we need, interstellar radius. But here, binaries, where the binary is contribution? Contribution of the binary is actually, it is light curve and radioplastic curve. We know the radii and temperature of the stars. And 2 stars, binaries, at least we have to, what is important here, each component of the binary contributes how much. We first separate only, then you can calculate apparent visual magnitude of each star separately. Then you can continue from there. A brief history for the bolometric correction. Hopper, 1959, just about 60 years ago, says the most recent comprehensive discussion about effective temperature and bolometric corrections is that by the Cooper, 1938. 1938 paper, it is really extensive paper. I looked at there, it is amazing. How many times they tried to calculate, they measured absolute brightness, absolute radiation of the sun, compare apparent brightness with respect to sun and moon and its stars, and he just revised it, and their temperature of the sun is taken to be 5,713 degrees, and look at that, how small, 13 degrees error. Error is very small. And apparent visual magnitude of sun is minus 26.7 magnitude, absolute visual magnitude 4.85, like that. Bolometric correction of the sun is taken to be 0, and temperature is 6,500 Kelvin. Lester 2011 says, in some ways, the photometric data of Bulletin paper are still fresh. Still today is still fresh. You can use that. What is the Bulletin paper? Bulletin paper says to Johnson, 1964 paper. This is just the paper 2 years before standard Johnson photometry defined, 1966 paper he defined, just 2 years ago, who gave the tables of supergiants and Main-Sequance results. This is the results, actually, how can you give them? Results of infrared program. It's the first time. Before Johnson, our observations was limited to only visual. But after Johnson, after this, the infrared program is 0.35 to 10 microns. So, ultraviolet and infrared is added. Then later, of course, improved radio and other parts. Here, we define magnitude and colors of the sun. You can see. Of course, before 6,500, now temperature of the sun is 5,800. Here, flower is the only one gives, he used parameters of 325 stars. This 297 have measured the effective and with reliable E minus D colors. 122 have measured bolometric correction and the effect. I used this data and gave two formulas. It is the first time it's given in formula. All these bolometric corrections, actually it's in the literature, only flower gives such formulas. The other bolometric corrections are all tables. These are valid for 2,900 degrees to 52,000 effective temperatures. Song et al. Reports Sejong Open Cluster Survey results tables for all luminosity classes, not only Main-Sequance. Here's the table. I believe he is here now, somewhere. Torres re-evaluate all these studies, announced 0-point constant errors. There is 0-point constant errors for bolometric corrections. And many published, there are published tables, errors, especially flower. And revises the flower equation and gives a 15-digit constants. You know, these 15 digits, you have to use 15 digits. You cannot cut just 6. If you cut 6, the BC bolometric correction cannot be calculated correctly. It is very difficult. And not only the temperature range, it doesn't work for the temperature range. 3 different temperature range. See? Different temperature range, 3 different, and one is 1, 2, 3, 4, 5th degree, 4th degree, and 3rd degree equations. And here, and also that there is wrong there. I have to go back. see B minus V, T effective. And there's something wrong. There's something wrong with it. Is not the effective temperature, function of effective temperature. It has to be, it's the function of B minus V column. So do not use Flowers paper, use fluorescent corrections. Here, we wanted to calculate bolometric correction from the binaries. We have the catalog. In fact, most recent catalog, published 2014, and the data is already in Vizia, you can go there. And standard parameters available in the catalog for 257 binaries. And catalog is updated. Now the stars are 319. Preliminary sample is from the updated catalog of attached double-line binaries. Total number of stars, 639. The binaries, how can be the odd number? It has to be even. Now, 318 binaries and 1 triple. So it was like that. But only 586 stars were published here. Some authors do not give effective temperature. They prefer to give a temperature ratio. Doesn't give the temperatures of each component. Here, the data is there. It's probably difficult to read. Heterogeneous to contain non-disk stars, non-main sequence stars, they're main sequence, okay, out of range metallicities. So we have to make homogenization. Refining the preliminary sample. This needs to be refining. Step 1, we removed 17 stars with mass and radius errors more than 15%. So, these errors are big, they remove them. Second, remove 12 stars, actually these are the 6 binaries, the globular star, globular clusters. Globular clusters are different metallicity, so it doesn't fit mass and radiation. So we have to remove them all. Then, study metallicity distribution, choose models accordingly, because we need zums and thumbs lines, zums and thumbs between the main sequence stars. We have to choose main sequence stars, so we need that. Then remove non-main sequence stars. These are the 47 stars also removed because they are out of the range of the main sequence. One star is, this is a special case, says this is strange. The primary is 10 minutes, okay, good. It's enough. So we, that is removed 77 stars. What is then 509 main sequence stars in the solar neighborhood? Within the galactic disk, metallicity is 0.008 to 0.040. Here, the metallicity distribution in the histogram form in the solar neighborhood, you can see the limits, lower and upper limits. These are the observations. We determined them from 72 stars, 36 binaries. So the peak at solar luminosity, solar metallicity at 0, but low metallicity limit is minus 0.3 dex. This corresponds to Z 0.008 Z. High metallicity limit is there. And zums and thumbs lines are from parsec models, present all. Here the removed stars in the upper. You can see that if there is, how can you show them? Here, there, in the lower line, it is, between them is a 0H main sequence and 10H main sequence, and between them main sequence. So we choose them according to, you can see, study sample of all main sequence in the disk, in the metallicity limit. How many? 509 stars. Mass luminosity relation of the study sample, when we did that, we can see mass-luminosity relation. Mass, logarithmic mass, and the luminosity there. Here, if you try to fit a continuous function, it is actually a 6 degree or a 50 degree or 6 degree polynomial you can fit. But the degree of the polynomial is arbitrary. You know, we can increase. But we try to see if it's okay. Rather than just single function, we can add up linear functions, classic luminosity. One line, another line, another line. So we see, we compare them. Okay. We compare them F-test and 6 classical mass-luminosity relation is equivalent to one piece polynomial of 5th degree or 6th degree degrees. So which one you prefer to use? Single ones and one after one another, or you have to use 6 constants and so many digits there you have to type. Here are the ranges: ultra low mass, very low mass, and intermediate mass, high mass. These are the domains, mass domains. Each domain has their own inclination. You can see that classical mass-luminosity relation there, and standard deviation, R-square value, and inclination there. Here are the relations. In ultra low mass, very low mass. You can see we put very well. And here, all 6 classes there. Mass radius relation and mass temperature relation is not possible for the full range, not like mass luminosity relation. You can see this is the upper part is mass radius diagram, lower part is the mass luminosity diagram. Here, mass radius diagram, you can see this one. No. Upper part, when the broad, this is the stellar evolution you see there. Now, when the star evolves, radius increase. So you have main sequence, very different radii. Only small mass stars, in the beginning, you can fit the function there. Maybe wrong part here. What's happening there? It has to be somewhere. So there's something wrong with the graphic. This line has to be, I can show that. This line must be quadric here. So this part upward, you can fit up there. And here, this part, you can fit for the temperature. Strangely, the numbers are equal. But this is logarithmic, this is linear. Just from this side in the upper to this side in the lower. We can have mass radius relation in the one. If mass radius relation and mass luminosity relation, we can calculate the mass temperature there. For high temperature stars, you have mass temperature relation, you have mass luminosity relation, you can calculate mass radius relation. Here it is. The calculations. These are interrelated: mass luminosity, mass radius, mass temperature relations, and data. All the stars, 509 stars. Nicely explained. You can see very broad part for the radii, and the low temperature stars, the wiggly line, it goes very good. And here, for the locus and mean values also there. The breakpoints, mass luminosity relation, are not arbitrary. They are stellar evolution models that comes in there. So, you know, we choose them. We didn't choose them arbitrarily. Actually, we discovered them before. You can see the mass, and here, log there. You can see the breakpoints. It doesn't go smoothly. It goes, breaks, goes, breaks again. And these are the three points here. In this new paper, we add 2 more, it becomes 5 breakpoints. Interrelated mass luminosity, mass radius, and mass temperature relations, fundamental relations, has been calibrated using basic mass radius temperature parameters of F9 main-sequence stars. In the revised couple, there were 53 stars with accurate mass and radii, but no published the effective temperatures. We did not use them in the calibration process. 34 of them, these are the numbers of 20 binaries, 34 stars, and 20 binaries, are on the main sequence. Now they could be used in computing bolometric corrections, because we have this mass luminosity, mass radius, mass temperature relation. So we add them 553 main sequence stars. These are means 283 binaries, at least one component on the main sequence. At least one component. We went over each binary to check its galactic coordinate and extension according to galactic dust maps. To check position on the bolometric curve. If a star has both Gaia and Hipparcos parallaxes, choose the one which is closer to the distribution. Some of the AVs, these are the 64 systems, suggested by galactic dust maps, were replaced by private determinations because they are closer to galactic disk. And some cannot be replaced because they could not find reliable source for them. Some removed because light contributions or components are incorrect. Preliminary samples of 225 minus 18, we have 207 system. These are the, copper is the preliminary sample. Here, blue dots, filled dots, Gaia data, extinction from dust maps. Empty is the extinction from other sources. And triangles are the Hipparcos distance, using Hipparcos distances from dust maps, and empty ones from other sources. Here, how can we choose calibration sample? Choose according to the most accurate parallaxes. We choose better than, relative error is better than 0.07. Here is the bolometric correction curve. You can see continuous single piece, like flower in the 3 pieces. It's a single piece in the temperature region, temperature 3,000 to 30,000. Here is the P minus P, T effective, calculated. Preliminary results. Bolometric corrections can be computed from a cubic function of T effective, valid for 3,000 to 30,000 Kelvin. Unreddened EV colors of main-sequence stars are also available as a function of T effective. Here we compare this study, the bolometric curve, the red one, to others. I cannot see from here, either from there. Johnson is the green one, 1966. And Flowers is the continuous blue one, and Song et al. Is the dashed one. You can see there are big differences. Yeah, they are agreeing, very points. Some points are agreeing, but higher temperature and lower temperature part is the problematic parts. And acknowledgement for this work into the
Thank you very much. Any question or comment? Timur?
It's just curiosity, how did you overcome the problem with A lambda extinction? A lambda. How did you overcome this problem?
Extension.
Yes.
The tensor extension.
Yes, because it's a function of color excess, and color excess has both it's actually addition of certain stellar material and also
it is given in Schlegel et al. Maps there.
Yes.
You know, if they have dust maps, galactic dust maps,
yeah.
actually first they calculate extinction, B minus V, excess. From this B minus V excess, you can calculate the axis AB.
But Schlegel et al. Gives the extreme color excess in the direction of the star. So, for example, you don't have any idea what's going on around. For example, it could be due to a circumstellar origin or circumbinary origin. So it doesn't actually give you an idea.
They also say that, you know, do not trust the
Let me just explain the situation a little bit. Because of the early break we had, I'm planning on having two talks, in this section, and then give a short, like 5-minute break, and then continue with the rest. So go ahead, please.
Thank you very much. Sorry for the technical problem earlier we had encountered. So I guess we all felt that we have to give a break. So in this sense, these rules always help us. My talk is actually going to be on hyperpromotion stars and sticking with the basics. And we will give some simple definitions, but I'm not expert in hyperpromotion stars. You know actually the famous writer Malcolm Gladwell and his famous novel Outliers. So one actually has, if would like to be specialist on one thing, at least has to spend 10,000 times, he says, this is his description. So this is actually simple with simple calculations. If we spend 8 hours on a subject, so for 5 days, or for 5 years, it takes actually 5 years to be specialist on some certain subject. If you spend 4 hours, then it takes 10 years. Then if you spend 2 hours a day, then it takes 20 years. So to be specialist in hyperpromotion stars, I should admit that I didn't spend 20 years on this subject. My main research area was CGP stars. I'm a classical spectroscopist, but we wondered how spectroscopy actually works with kinematics and dynamic information in terms of determining stellar populations. And of course, there will be further results on this. So, we would like to present our research and as a case study on hyperpromotion stars. This has been performed in collaboration with Professor Salih, who is organizing also this meeting. Also, we have hidden collaborators, Olcay Pleyne, second year PhD students, and he's also local organizing committee member, and Gizay Ololan from Akdeniz University. She has recently graduated and completed his master thesis and started PhD program there. So, in terms of motivations, we may actually list lots of things. So, one of the things, their galactic origin. What are they, these stars? How do we define these stars? And what is the source of their hyperpromotions, and so on. So, we have, as a method, high-resolution spectroscopy, and we use as tools kinematics and dynamics. So I will give some brief description of HPM stars, and then the spectroscopic analysis we have performed, some details on this, and then some details on kinematics and dynamics, and I will present results and finish ending my talk with concluding remarks. Of course, please don't expect me to give each and every detail on these titles, but we actually currently submitted this to Montpinosis and waiting to hear from referee, so fingers crossed. Let's start with Gaia proper motions. Professor Gilmore, this is actually the last slide of Professor Gilmore, maybe slightly different version. So what we see is actually combination of parallax and proper motions, but parallaxes have been exaggerated 100,000 and proper motions by 1 trillion. So we are looking at it exaggerated image. So it's not possible to distinguish parallax and proper motions, but if you stick to basics, it is a function of distance and radial velocity of the star. So what we call proper motion is projection of stars through motion across the sky, or angular motion of star simply. What we have done, there are lots of libraries available. So we start with LOD and then looked for F spectral type stars. Why? Because are mainly trans and FGK type stars. And then LOD is actually providing such an opportunity. So we found 625 F spectral type stars. And then these all have HPM designations. I actually will call high proper motion as HPM through the rest of the talk. And then we also checked for binarity. So for any information on binarity, these have been actually removed, rejected, elected from the list. And then we have whole HPM sample that consists of 54 F-type stars. More on to this, we also looked for selected only metal poor ones. So this is actually temperature range for our stars. I think laser is reflected. Anyway, so the gravity, the range in the gravity you see between 1.7 and 5, and the metallicity goes down to -2.4, where I think Gaia template spectra, we will have problem with Gaia template spectrum to find the template spectrum in this metallicity region, as George Seabroke presented beautifully in his presentation. And then distances between 9 and 283 parsecs, the distances. Among them actually, we specifically focused on the stars, HPM stars, the F-type HPM stars, with the metallicities between -2.4 and -1, because these stars actually not selected in earlier studies. This was the main reason, and how we selected our sample stars. So in total we have 6 of them. These are the plate number of stars, HPM stars, galactic coordinates, galactic latitude and longitude information, and the spectral types are listed. And exposure times, this is actually kind of also confirmation for, there was a talk on small telescopes and how they are useful for galactic studies. So if you accept LOD OHP 1.9 meter telescope with LOD spectrogram as a small telescope, and this is also corroborating the same talk, the same name. So these signal noise ratios are also listed, and then heliocentric velocity is reported in their header, is also listed in the last column. So they are high proper motion stars, and proper motions in right ascension, in declination, the ranges are also given to the right of the tables. These are indicated with the color. The reason actually I've chosen is to specifically to explain, to give some further details on the analysis. I'm not going to get into detail for each and every 6 stars here, so this was the main reason. Okay, let's see here. We have a little spectra chosen from a little library, and then the first stage was to perform continuum normalizations, because as you all know, LOD spectra has issues with continuum normalizations, because this TGMAT software, this is at the telescope, this process, actual reduction process, is performed at the telescope, but during merging stage and normalization process, some issues. So one has to make a correction for normalization, and then this is actually performed with in-house developed ideal package. LIME stands for line analysis and measurement formation spectra, and then again we perform line identification in this code. Atomic data compilation is important stage for any spectroscopic studies, analysis. So what we have done, we simply, by using our atomic data, try to reproduce solar evidences. So this gives an idea what is our zero level in each evidences of every element. So the reproduction of solar evidences was successful. Of course, there are alternatives. You could also compute astrophysical log GF, and on the basis of this atomic data, you could perform the rest of the research. So model parameters, of course, one has to decide which lines to be used for model parameter determination. When I say model parameters, I mean effective temperature, gravity, metallicity, and macroturbulence velocity. This is turbulent motion in the atmosphere, small scale turbulence. And all the models are 1D. We also perform tests with 3D stagger models. And Atmos script is already available on the net. This is a 1D version of 3D LT hydrodynamic stagger model atmospheres. But this has been simply performed at the beginning with Atlas 9 models, which is typical. But we also did some tests with Mark's models. So here is actually just to give an idea. To the right, you see line profile shapes. This is just to show for BD plus 42, 36, or 7, this is the most metal poor star in our sample with a metallicity of minus 2.4. And this is very low metallicity. And then you see the line profiles of selected neutral and ionized ion lines. That's just to give you an idea which lines were used in determination of model parameters. And then at the bottom, you see the methodology, actually, graphical representation of methodology that we use in the model parameter determination. To the left, at the upper plot, you see abundances versus lower excitation potential plot. This is a kind of excitation balance plot. So we search for temperature. And then in the middle plot, you see abundances versus lower excitation potentials, but this time ionized ion lines are included and their appearance. And at the bottom plot, in the x-axis, you see reduced equilibrium width, and in the y-axis, again, abundances. So these all three actually conditions gives you, on the basis of excitation and ionization balance equations, effective temperature, gravity, microtubulous velocities. So the same graphical illustration is also given for HD 194. And then the next stage is actually computing chemical abundances on the basis of this model parameters. Okay, so we have model parameters obtained and by using the Atlas 9 model atmospheres, and we did not only use economic analysis. There are two common methods. You can either use economic analysis in order to obtain chemical abundances, or you could do spectrum synthesis if you suspect hidden blend features in the spectral lines. So we actually perform both. This is kind of this is example for selected line profiles. You see some S process elements and strontium, cobalt, zirconium, and for our process dominated element you see barium, and also selected carbon line profiles, and computed abundances with spectrum synthesis technique. Is it that simple? So, did we do? And is it all done? It's not actually. We are studying, we are working with metal poor dwarf stars. And if you are working in a metal poor regime, then you have to be careful with ion lines, which ion lines you have used. The problem is low excitation ion lines and high excitation ion lines give different abundances. So since you obtain effective temperature on the basis of excitation balance of ion lines, and also you have an assumption LTE, this means you also have to provide Salih and Boltzmann equations also has to be corroborated, or has to be set in this regime. But one also has to check whether low excitation potential ion lines give higher abundances or not. Our test, in addition to this, hyperfine structure and also isospin effect has to be included when reporting chemical abundances. This low excitation ion lines and high excitation ion lines, the abundances computed from those two groups, only differ 0.05 tex, so which is negligible, and so this actually proved to be positive. Then let me continue. These are the model parameters obtained for the stars. By the way, these stars are actually well known and well studied in the literature, but we have up-to-date atomic data, and also we improved the model parameters in the sense you are looking at recent model parameters. At bottom, this is actually model parameters for sun. This is our computation from solar spectrum. Kitt National Observatory solar flux data has been used for this process, as I mentioned earlier. So we had to reproduce solar advances in order to test our atomic data when we determine our atomic data. I actually put this table just to show we were able to find Gaia temperatures. So we also report model parameters for Gaia template, synthetic templates to the left in the second column. So, and then our temperature determination is given in the fourth column. So if you compare third and fourth column is actually temperatures given by Gaia. For example, for BD plus 14, you see the difference around 400, 500 degree Kelvin. So, but this is actually something to do with BD plus 42. Also for HD 84937, you see that actually temperature difference between Gaia temperature and temperature in this analysis is around 390, 400 Kelvin again. Again, this is something to do with the star itself, HD 84937. I will explain this in a bit. For the kinematics and dynamics part, UV and W space velocities have been computed with actually common algorithm of Johnson and Southern law. Then proper motions and trigonometric parallaxes are from the Gaia DR2 catalog. And we also obtain radial velocities from LOD spectra. We also give some information on relative parallax error. And for these actual space velocities, differential rotation corrections also were applied, and then space velocities were also corrected for LSI. So these are computed space velocities. U, V, W, and S in the last column represent total space motions, total space velocities. So when you look at this table, 5 of these stars have total space velocities higher than 250 km per second. This you can actually see the same in the Tunre diagram, which is given in the bottom. You actually see the contours for constant peculiar space velocities. When you look at the 4 stars to the left, so they all have total space velocities higher than 250 km per second. So just to remind that these are high proper motion stars. Also they are actually high velocity stars. And these 5 stars that I actually mentioned have total space velocities higher than 250. And we also try to determine their populations. So if you stick to bandspline criteria given by TD over D ratio, TD for probability for thin disk and D for thick disk. So on the left-hand side, you see high probability and low probability, the ranges for high probability and low probability for thin disk stars. And to the right, you see TD over D ratios for thick disk stars and for high probability and low probability respectively. The relative probabilities are actually computed with these 2 equations. TD, the probability for thin disk stars, simply computed, calculated by local number density multiplied by probability F. F is a function of velocity dispersions in U, V, W space velocities, and is also a function of drift velocity, and is also a function of U, V, W space velocity components. So in terms of bandspline TD over D, TD over H criteria, these 5 stars, these all actually 6 stars, are greater. They have TD over D ratios larger than 10. So this actually shows us these stars are halo members of halo population. if you follow Nissan's 2004 criteria, Nissan gives criteria on the basis of their total space velocities. For example, for thin disk stars, if a star has a total space velocity less than 60 km per second, it's likely member of thin disk. And then if it has a total space velocity between 80 kilometers and 180 kilometers per second, then this is probably likely a thick disk star, and so on. So on the basis of Nissan's criteria, you have 5 stars in the sample, and they appear to be the Hell members, and 1 star is appear to be a member of this population. So which one to believe, right? Let's continue. In addition to kinematics, we also computed orbits. So these are graphical illustration of orbit computation for selected sources. Again, HD 3567 and HD 194 and HD 201. So the projection of the orbit in X, Y, and XZ planes. So you have orbital parameters. So one thing to do is actually to look for see the Wheeled stars in Zmax EV plane. Zmax is this is actually maximum distance from the galactic plane, and EV vertical eccentricity. So if you plot Zmax versus an EV, you see the plot at the bottom. For example, 4 stars appears to be thin disk on the base of their appearance in Zmax EV plane, and 1 star appears to be a member of thick disk, and 1 star again appears to be halo. So the underlying 4 stars in the table at the top, starting with HD 201, HD 194, HD 35, and HD 84, these all appears to be thin disk stars on the base of this orbital parameters, but interestingly they have planar eccentricities higher than 0.5. So now we have 3 findings in our pockets. We also computed their ages, and this has been performed with isochrone matching. And for this aim, we use parsec stellar evolution models. This is the actually stellar evolution models used in the grid. Metals, you see the metals range from minus 2.2 to 0.05, and then also range in the age. Step sizes are also 0.05 and 0.1 gigayear respectively, in metal states and in ages respectively. So here is actually you are looking at LT model parameter, position of LT model parameters in effective temperature and gravity planes for each program stars. Okay, if we summarize what we have so far, on the base of ages and metallicities, then with these criteria, you have 3 stars that appears to be members of halo. And then again, HD 35, HD 194, and HD 201 appears to be member of thick disk stars. But if you stick to galactic orbital parameters, then for HD 67, ED plus 14, they appear to be halo stars, and HD 35, HD 201 appears to be thick disk stars, and HD 84 and HD 194 appears to be thin disk stars. The last 2 is actually has important properties. I think we should note that. So they have distances. The maximum distance from galactic plane is around 400 parsec. So, but when you look at the metallicities for HD 84, it has a metallicity of minus 2.4, which is contradicting with its actual membership. And HD 194 has a metallicity of minus 1.2. So, which is interesting also to note. Did you get bored? Do you still want to continue? Okay. Really? So the main question is actually, okay, so these guys have performed classical advances analysis with classical atomic data that everyone can reach from the internet, or NIST or VOLT atomic databases, right? But the problem is, these stars are high velocity stars, hyperpromotion stars, and somehow they have been accelerated to such high velocities. But how? So if you look at the theories, two-body or three-body or more-body interactions are listed reasons in the literature. Tidal interactions in a globular cluster or galaxy interactions is listed as a possible source for their HPM nature. For these two or three body interactions, you need dense cores of globular clusters. These are most likely sites for such reactions to occur. Also, the binary fractions and encounter rates are also higher in the core of globular clusters. So I think the binary fractions between 1 and 10 reported by Jeremy Webb, right? Okay, so what we have? So we have done some simple tests. We have edges, we have metalicities, we have orbital parameters. So what we have done, we have searched for obtained metallicities from Harris catalog 2010 edition. And then we obtained up-to-date model parameters for globular clusters, 167 globular clusters in our galaxy from Helmy et al. 2018. So, and we searched for, okay, which of these stars and these globular clusters have...
Is that something that you...
We did actually this test for a couple of stars.
Yeah.
The problem is actually with radial velocities. So, radial velocities.
Yeah.
Yes. Because you get close encounter, but you have to decide what should be the range for radial velocities. In what radial velocity range one should look for encounter possibilities. I think we have to start with, claim that, okay, this star belonged to, or belonged to this globular cluster. Let's compute encounter possibilities, how many times they get closer, and then whether the star's velocity, visual radial velocity, is compatible with that. So,
yeah, sounds good.
Let me just thank the speaker one more time. The role of stellar chemical evolution models in galactic research.
Hi, I'm Tolga from Ankara University. Before I start my presentation, I'd like to say that I'm not expert in galactic astronomy, but I know that many information needed to trace the galactic chemical patterns come from the stars. So in this presentation, I'm going to talk about the problems of modeling stellar photospheres, as well as the current situation of chemical evolution, stellar chemical evolution models. So stars are basically K objects to trace the galactic abundance gradient. But to do that, we cannot use the old spectral types because we need stars with photospheres well mixed with their interiors, because we are looking for chemical composition of their birthplaces, not the stars themselves. So what spectral types can be used to do that? For example, very early type stars strongly affected by stellar winds, which should be carefully modeled. Early B-type stars have moderate winds, which mix the material inside the photosphere. So this is a good thing. In this way, we can obtain pristine abundances of the stars. However, late B-type, A-type, and early F-type stars are strongly affected by diffusion, and diffusion also disturbs the abundances. And late F-type stars also has convective envelopes, which mix the material in the photosphere well. And in contrast to the early type stars, they have also a larger number of lines in their optical spectra. So this allows us to find the chemical abundances of many different elements. G-type stars may also have a strong magnetic field, so one should be careful while working on these stars. And K and M type stars might also have a magnetic field, and also their spectra are dominated by molecular bands and line blending, which make it really difficult to study their spectra. Well, and model atmospheres. What model atmospheres we can use to model these spectral types? There are many model atmospheres in the literature. I've just listed 10 of them, and I'd like to show them on HR diagram here. For example, the well-known model atmosphere called Atlas can be used for the intermediate spectral type stars. Atlas can also model the hotter stars as well as the supergiants. But since the code assumes the local thermodynamical equilibrium, it's not so meaningful to use it for hotter stars and supergiants. And for cooler stars, there's another code, MAX, can be used. And also, Phoenix is present for much cooler stars, and it's very sophisticated model atmosphere code. For the coolest region, there's a special code to model the convection of the stars in detail, and this code can also be used for warm dwarfs and white dwarfs as well.